in Electronics and Telecommunication Engineering from University of Pune. He has various experiences on various posts like Dean. Currently, he working as a Dean, School of Electrical and Communication Engineering at COEP Technological University. He work as an associate professor. He has total 31 years of working experience. He guided almost 82 PG dissertation projects in the area of image processing, in the area of embedded system. He is a recognized PhD guide at COEP Technological University, Pune. He works as a coordinator with Center of Excellence in Signal and Image Processing at COEP Technological University, Pune. He published around 55 technical papers in international and national journals and conferences within and outside India. Also attended several international and national conferences. He worked as a resource person for the various workshops organized by the host departments. He delivered various lectures in the area of signal and image processing and also attended many workshops. His area of interest mostly in the area of signal and image processing, machine learning, deep learning, embedded system, and computer networks. He worked as a member for various committees related to computerization of centralized first year engineering admission in the states. So with this, I welcome our today's resource person, Dr. Prashant Bartakke, sir. Over to you, sir.
Thank you. Thank you. I think Navnath Bhosle, sir. Okay.
Now you are
So,
host, sir.
yeah.
You are
Okay.
host, sir, now.
Yes, sir. Yeah. Yeah. I'm host. Okay. Thank you. Let me first thank the organizing committee, Dr. Javed Sheikh, Principal Mukane sir, and all the organizing members for giving me opportunity to speak to you. Initially, the topic was different, but I suggested to change this topic to automotive communication network because thing is, I really wanted to share my experience or whatever I know with you regarding automotive communication network. So even though it is, directly we are jumping into automotive communication network, uh, mostly I feel that there are no prerequisite required. I hope that many of you are yeah, faculty members. Is it the case? And I think many are waiting in the waiting room. Mostly, sir, you can admit them.
Yes, sir. Yes, sir.
Yeah,
I
so
will
that
admit
message is popping up at my end.
them.
Yeah, okay. Okay. So thing is, the background is you have some communication background. You must have worked on some buses, some communication, and we all understand importance of communication network, communication stack, and so on. The very, visible kind of application is the this online talk itself. This is one of the manifestation of communication, the like entire software stack, communication network, the internet working together, all of binding us together and makes us feasible to talk to you. I'm in my home, you are at your homes, and then we are discussing something which is of interest to us, I hope. And let's understand like one more interesting stuff, which is automotive communication network. And we will not be going into details. Mostly it is combination of this embedded system, communication network, buses, and protocol stack. So it is all about that. So I would like to brief you about that, and maybe I can appeal you, I can suggest a few platforms to you so that you can really practice it, you can really implement it and see it in action and function and so on. So with this initial background of the topic, let me show the screen, let me show my ppts, and later on I'll be sharing the ppts with you for your reference and further understanding and further exploration of this topic. So let me share the screen. Let me share the window. Is this window visible to you? Is the window visible? Am I audible? I hope that I am audible.
Yes, sir, you are audible.
I am audible. The screen is being shared,
Yes,
and
yes.
you can see the topic. The topic is automotive communication network. We'll understand a few things or properties of CAN, which is a traditional communication bus used in automotives, and slowly it is being, I mean, the entire industry is being shifted towards automotive Ethernet. So we'll see what are the reasons, right? What Ethernet facilitates, right? So that people are slowly shifting to automotive Ethernet, and maybe in the 5 years down the line, or maybe 8 years down the line, everything will be automotive Ethernet. So that is what is importance of this topic. So that's why I feel that instead of maybe having an general overview of communication network, let us have this specific topic and pass on the importance of automotive Ethernet with you all, and so that you can have your whatever research or your career in this domain. That is what is the intention. So let us start. So thing is, this is once again good evening. So we'll be discussing this automotive communication networks, traditional CAN versus automotive Ethernet. Why people are shifting towards automotive Ethernet, and before understanding that this shift, we'll understand what are different features of CAN, what are limitations of CAN. That's why people would shift to automotive Ethernet. Or I mean, maybe this is the era where both the networks will coexist, and then later on this CAN will be wiped off, and then automotive Ethernet will take place of CAN. So that's what people think. Let us see what happens. By the way, if you have some question, you can ask. You can note down my email address, and you can ask questions on email or maybe directly by unmuting yourself. If that is available with you, that feature is available with you, you can unmute, or you can type in this in the chat. The organizers will read, and towards end of this session we will have maybe answers of whatever questions or whatever queries that you have. Okay, so let's move on. So thing is, what's there in the modern vehicles? Let's understand it. So the electronic content, and these modern vehicles have a lot of electronic content. So as that is listed, it has now, the most modern vehicle has hundreds of microprocessors. So that is very important to understand. All of us know that there are electronic control unit, what is called as ECU, which are either based upon microprocessors or microcontrollers or system on chip. And these are not standalone systems. Understand? So these electronic control unit are not standalone system. They are networked together. So obviously, I mean, I would like to get your attention, right, from this standalone system towards this. And the focus of this session is really networking aspect, the bit rates, and the requirements, what kinds of application it will facilitate, and so on. So slowly we'll move our focus towards networking and the shift. But I want to lay down the context so as to understand importance of automotive Ethernet. And thing is, if there are hundreds of microprocessors, what is the order of, I mean, lines of codes that goes in programming these microprocessors? Some numbers are quoted, plus minus hundreds, 100 million lines. 100 million means how many crores? Anyone? 100 million means how many crores? 1 million means 1 million means 10 lakhs, right? Multiply by 100. So 100 million means 10 into 100. So 1000 lakhs, right? So 1000 lakhs means 10 crores of lines, right? 100 lakhs is 1 crore. So 10 crores. So just to know the scale of lines of codes that goes in the programming microprocessors, this is the scale. So thing is, the if you really wanted to understand why, what is the importance of this topic, we can just have a look at this cost of the what like modern vehicle. So I think the cost of this electronics that goes in the modern vehicle is around 45%, 45 to 50% of overall cost of the vehicle. So try and understand, guys, the importance of this topic. and what is the scale of this topic and what is the importance of this topic. Okay, so that is what is the scale and that is what is the value that we want to bring in, right? And then communication network is very important part in this electronics content, because these microprocessors or SOCs doesn't function in standalone manner. They communicate, and there is need for communication. Okay, so thing is, even in conventional automobiles or automotives or vehicles, the electronic content is around 30%, plus minus. These are statistical figures. It is around plus minus 30%. So huge, I mean, part, right, is present. Huge electronics part is present in this modern vehicle. And uh, can anybody correlate with importance of this or this? I mean, like presence of this much portion, right, in modern vehicle. You must have seen that in COVID, where there is scarcity of these chips were not getting imported. So what used to happen is this pipeline, the delay in delivering vehicles was huge, and the one of the main reasons, right, in the delay of this delivery of vehicles is this: the chips were not available. So if the chips are not available, ECUs were not getting built, and if the issues are not getting built, most of the features or many of the features were not been incorporated in modern vehicle. So that is what is importance of this electronics content. That's once again I want to focus on. So thing is, I mean, then and we have now EVs, electric vehicles. Okay, so new electronic functionality will continue to be added every year, right, for the foreseeable future. So new and new features are getting added. The thing is, what we would like to stress upon is this component, which is the portion 45% or 30%, is going to go up. And by 2030, right, it is projected that the cost of the vehicle, right, and the cost of the electronics content in the vehicle is almost 50%. So 50%, or it may cross 50%. Okay, so that is what is the uh, like the type of weightage that should be attributed to this electronics content. The thing is, as I said, this is easy to understand, so I will not wait over here. I'll go ahead. The thing is, what is this? Is the same thing is being projected. This is in 2030. It's not, the x-axis is not visible. I'll slightly minimize it. Yeah. So this is around 2030. You can see that this is exponentially increasing, and around 2030 you can see that the cost of the vehicle is around, I mean, the cost of electronics component in the vehicle is around 50%. So that is what is importance of this, I mean, electronics content. And once electronics contents are there, once several electronic, I mean, control unit, ECUs in short, I mean, short, once again I'll specify ECUs. Once those ECUs are present, they are networked, they are not standalone. So they are network. And once, I mean, they are network, all, I mean, the requirements of network, the capacity, the bandwidth, the physical layer, and the higher layers applications will come in the picture. And that is what is the precisely this core of this whatever today's lecture. So thing is, this the same thing is been written over here. They are not independently functioning. The ECUs are not independently functioning, but thing is, they, I mean, communicate with each other and they complement each other. The thing is, that is what is the case. And then what we have is day by day our feature, and once the features are more and more features are incorporated, more and there's a requirement of increasing the bandwidth, right? So information, more and more information is getting shared between these ECUs. That gives rise to requirement of increase of bandwidth. So thing is, so that's why, I mean, this why there is this electron, the automotive Ethernet is born, is out of this requirement. So we'll have, I mean, the sequentially what was there, right, in or what is there in automotives. So it started with CAN. Initially, when there were handful of ECUs, they used to connect it directly, and it was just, I mean, the solution that was available, some ad hoc solution that was available whenever there are only two or three ECUs available. But as number of ECUs grown, the they felt need of some communication bus. So that's why that gave birth to this CAN. So CAN is controller area network. CAN is controller area network. It was introduced in 1991, and there are many versions of CAN. CAN B, CAN C, CAN flexible data rate buses, right? So where CAN B is low data rate, CAN C is higher data rate, and so on. So thing is, so large volumes of data from different sources can be transferred. So we can now have, instead of having, let's say, 2 or 3 ECUs, we can have number of ECUs, and the data can be transferred between these ECUs. We'll understand in detail how the data can be transferred and what are at what rates and what are requirements at physical layer and what are upper layers. We'll understand, and we'll understand this communication network. Communication network does not really mean that only physical layer. Upper layer are also important, so that it is all about developing applications, guys. And to develop application, we do require a stack, network stack. And once the network stack is available, we can develop application, we can customize application to suit to the needs of applications. So we'll understand, the focus is understanding even physical layer and understanding upper layers, and understanding how these upper layers help in developing application. So that is what is this CAN. And then this whenever, the requirement was not really very stringent, where low speed, where the requirement is of, this low speed CANs, where the requirement of low speed exchange. So the LIN is local interconnect network is LIN. So this is an alternative to the low speed CAN. So it is, the speeds are of very, of the range of 20 kbs, 20 kilobits per second. So speeds are very less, and it is possible to connect 16 such devices on this lane bus, where the speeds of CAN B are of the order of 250 kilobits per second. CAN C may be of 500 kilobits per second, and CAN FD is still further higher. So it is in hundreds of kilobits per second. So whenever there is a requirement of low speed, we can have the version of this alternative for CAN, which is local interconnect network, which is LIN bus. And then we have this most bus. Most is media oriented system transport. This most bus, which was there for infotainment system in the vehicles, or networking of infotainment system, which are the players and there are displays. So if we want inter networking of this infotainment system, we can have this most bus. Most bus is media oriented systems transport, and the speeds are, of the order of, most 25, most 50. You can read the speeds, which is 50 megabits per second, or most 150, which is 150 megabits per second, and so on, which is the requirement in case of transferring media. Media is audio or video or some other, maybe images and so on. So that is what is media is, especially audio and video, right? So for, the communication between all the devices which are concerned with streaming audio or streaming video, the bus used is most bus. And the next, another one more bus is this flex ray bus, right, which offers this guaranteed compliance with transfer properties and high bit rate. And this bus is a fault tolerant bus. So when in case of the safety system, in case of whenever we want active safety system or transfer of even audio or highly compressed video, we can use this flex ray bus. And finally, nowadays what we have is this automotive ethernet bus, right, where the speeds are quite large, right? In the, this is, there is a typo, 100 megabits per second or 1 gigabits per second are the speeds. And why is this requirement? You can see that we now have this ADAS, which is advanced driver assistance system, right? So one example of this ADAS is maybe lane cutting detection, or reverse parking, or auto cruise control, or maybe obstacle detection, and so on, right? The thing is, that where there are levels, ADAS 0, ADAS 1, ADAS 2, and so on. So as levels increases, this complexity increases, which requires many cameras to be connected, like capturing images, cameras or lidars or other such devices are connected, and then in which we require this speed of transfer, right? which is higher, like of the order of maybe 100 Mbps or 1 Gbps and so on, right? So even, I mean, it is used in infotainment system. So more and more such things are coming up, right? So where we have Bluetooth and connectivity of Bluetooth to the infotainment system, and then streaming of, or maybe we can have Wi-Fi, or we can have, I mean, 5G connection or 4G connection, your navigation and so on. So lot many features are getting, I mean, incorporated in vehicles, which do require this automotive Ethernet to be present to support all these applications, right? So thing is, that is what is, I mean, this is, I mean, this is a brief, I mean, incremental chronological, I mean, evolution of uh, automotive communication networks and the buses used. So before moving on to this CAN, so any question, any comment that anyone has based on this?
Good evening, sir.
Yes.
Myself, Dr. Raghavendra from Mysore, Karnataka. I'm speaking.
Okay. Go
Sir,
on.
I don't much knowledge about this one, but
Mhm.
I'm in the field of communication.
Yes,
So right now we are using automotive Ethernet, sir.
correct.
The
Yeah.
okay,
So thing is, I
uh,
mean, many advanced vehicles are using, right?
okay,
And this
uh,
automotive Ethernet is being used in the backbone. Slowly, it will percolate to many other ECUs. I'll show you the figures, the possible architecture and the figures.
thank you, sir. Thank you.
Okay. Okay. So that was a good one. So it's required to break the monotony and to get into some interaction, so that I really understand that, I mean, you people are listening to whatever that is being said here. Okay. So let's move ahead, and let's, I mean, very briefly, maybe invest 15-20 minutes in understanding CAN and how the communication happens and what is importance of this higher layers, right? As I said, I mean, all these layers are very, very important so that we can develop application. Okay, so communication only means, does not mean that physical layer, right? Now we require, most of the time physical layer is readily available. What is important is develop application using all the layers including physical layer. So that is what is important. Guys, remember that, if, I mean, if you really wanted to do core research, then you can go to physical layer or some other layer, the lower layers. But if you want to quickly develop application, you need to understand this entire stack. Only then you can develop applications. So the efforts are to understand this entire stack to some extent, and, I mean, we'll give some pointers for you to study so that you can go ahead and study it and then build yourself, prepare yourself, I mean. Okay, so let's go through this CAN. So thing is, this, the electronic control unit looks like this. Broadly looks like this is, I mean, slowly will be moving away from embedded system. Just to get into this embedded system have been uh, shown on this slide. So we have ECU, where the most important part over here is microcontroller. And then in addition to this, digital or analog inputs, outputs, and the software which is written for these applications running on this microcontroller. What is important part over here is this, these controllers, the CAN controller, the lean controller, multiple such lean controllers available. Okay, so thing is, nowadays this ECUs do support these, I mean, it has native support for CAN communication. So CAN controllers are available, lean controllers are available, which will drive this CAN bus or which will drive this lean bus. And then we can connect the devices which are CAN compatible, or we can connect ECUs, right, which are CAN compatible. And then if I connect ECUs to this CAN bus, they can they can communicate with each other, and collectively it is possible to do some, maybe have some inferences or have some control mechanisms and so on. So that is what is intent of this communication. At least have some status, maybe what is the tire pressure, or what is the temperature of engine and so on. Or maybe if you want to have some control, maybe some, maybe uh, let's say think of power window, right? So let's say if you want to get it up or down, right, we can communicate using this maybe lane bus and so on. So broadly, it is this such kind of underlying platform is available. Okay, and then what this is, once again, I mean, some information that is available, maybe you can ignore this. What is important is this: there are these interfaces which are available, which is, I mean, the CAN port available, there are LIN ports available, multiple such ports are available. And maybe one such example is shown over here. It's just one example where, let's say, we want to control these exterior lights, maybe lamps, headlamps, and so on, or interior lights, the lights in the cabin. If you want to control, we can have, I mean, communication using maybe LIN bus and so on, right? If you want to have a control of wiper or washer function, right, or maybe power window control and so on, we can have such applications implemented or controlled using such kind of interfaces. Right? So maybe it might require this OZEC kind of open source operating system, right? So the thing is, we can have such platform available and we can implement applications like this. So how these are connected? So then there are many applications which are listed. So we'll have lot many ECUs controlling many of such applications, and applications, safety applications like airbags, right, braking systems, and so on. So lighting system, right, steering control, stability is very important. What is the speed? And based upon this, we have to control this entire moving body. So stability control, right? So tire pressure monitoring system. So many applications for which there are ECUs available, and then ECUs would communicate, and I mean together the functionality can be implemented. Okay, so this is just an thing is. So thing is, I mean, we'll now understand about this CAN very briefly. We'll understand fundamentals of CAN communication. This is the agenda of CAN. So what are layers, right? How arbitration happens? What is the need for arbitration and so on? We'll understand, and what is the frame format and how we can implement this, right? So maybe implementation part we might skip. I'll just give you the pointers for you to implement. Okay, so the thing is, we'll understand this CAN B bus, which is a low speed bus. Okay, so this low speed CAN we'll understand, which operates at whose standard is this 118983 standard, ISO standard. The speeds are 5 to 125 kilobits per second are the speeds. Okay, and most of the applications in comfort or convenience body area, such CAN B buses can be used, for which, I mean, this much speed is sufficient enough. Okay, so thing is, many applications using this buses are mentioned over here. Maybe this mirror adjuster or lighting system, right, or maybe seat adjustment and so on. Such things can be implemented by using, by communicating and then controlling the actuators which will really do seat adjustment, or which can get really the, I mean, window, the glass of this window up or down. Okay, so this is the way the ECUs can be connected. So we can have this CAN B bus. This is the CAN B bus. Several ECUs can be connected. You can see that why it is a bus, right? Because it's a bus like, I mean, structure where all the ECUs are connected to this bus, right? So it's a looks really like a bus, long bus, right? So a pair of wires, these are pair of wires. There are two wires which will rename those wires or will label these wires. So several ECUs can be connected. Several ECUs, I mean, the thing is, try and understand that several different versions of CANs can be presented in a vehicle, and then we can have a device like gateway for communication between a ECU on one side with ECU on the other side, or vice versa, right? As well, we can have a diagnostic, I mean, interface. Remember that it's a vehicle, right? The vehicle, who is supposed to use vehicles? Human beings. So safety is of prime importance. So testing rigorously happens, for which we do require this diagnosis interface, so which can be used for testing or fault finding and so on. So we can have this interface, we can tap right at the gateway, and then we can really capture the communication that is happening between all these ECUs, and then we can diagnose the problem. So this is the way the devices are connected. So that's why it is a bus-like structure. So this topology, this or the structure, topology or structure is bus-like structure. Okay, is a bus structure. Any question on this? Just to break the monotony, any question? You can, just say, okay, understood, and then we can move ahead. Okay. So if there is no reply, we can go ahead. Okay, so thing is, this is the internal. Just look inside a node. So the node looks like this. We have a microcontroller, and then we have this CAN controller. Remember, understand that for driving the information on the CAN bus, we do require this CAN controller. And this CAN controller communicates with this CAN transceiver by using pair of lines, which are called as CAN transmit data line and CAN receive data line. So we have this CAN TXD RXD lines, and the real bus, the actual bus, is driven by this CAN transceiver. So this is supposed to implement physical layer of the CAN bus. So this is supposed to implement physical layer of the CAN bus, which drives CAN high line and CAN low line. So this is CAN underscore H and CAN underscore L line. So this is what is CAN bus, and several such devices are connected. So thing is, the role of this device is to sense data. Maybe think of tire pressure sensor. It is supposed to sense data, and maybe it can transfer this data to a device, to a central device, say central device, which can read the CAN frames containing this tire pressure and can display on dashboard the tire pressure. Right? So your dashboard for information of driver, right? So to communicate with the driver how much the tire pressure, so that he can drive the vehicle carefully. Right? Or maybe it can receive information from other device, and based upon that information it can actuate the, I mean, it can control the actuator which does some task. Right? Thing is, so maybe turning on the light or turning off the light or dimming the light. So based upon that, it can actuate the uh, output device. It can be motor or LEDs or some maybe valves or maybe some relays and like that. Okay? So those are actuators. So this is the internal architecture. Okay. So thing is, what we have is whatever that I spoke is given on this slide. So I'll give a minute for you to read. So what we have is CAN controller, CAN transceiver. Okay. So thing is, this CAN controller is responsible for transmit and receive. So CAN controller generates bit stream for data communication, which is communicate or which is forwarded to this CAN transceiver via this TXT line. And then CAN transceiver amplify. This is important. It's a physical layer. This is what is we call as physical layer, where this CAN transceiver amplifies the signal if required. If required. So does, you must have under having knowledge of line encoding or line coding. So this is some form of line coding. So if the bits are received, how to convert those bits into signals. That is the role of this CAN transceiver. And we'll understand what are these signals, how it is supposed to generate the signals. And what it does is, this CAN uses, very important thing is, CAN uses this differential signaling. So differential data transfer. Right? We'll understand what is differential data transfer. That is why these lines are there, CAN H and CAN L. So this CAN H and CAN L, differential signaling is used. So differential signaling, the reason being, thing is, in case of vehicles, there is a lot of noise. There are vibrations, noise, and so on. Right? There is spark that is happening. So a lot of electromagnetic radiations are there. So in the form of that, there is a lot of noise. Right? And then in the presence of all mechanical vibrations, this noise, the communication should reliably happen. So for reliable communication, what we have is differential signaling. That is why this CAN is very popular and CAN achieves reliable communication. In case of this, lot of noise. In the presence of lot of noise. That's what I mean. Okay. So what are these? Labels. The labels are this. Let's concentrate here. and I'll show you the figure immediately. So the bits, the logic 1, which is transferred via CAN TXD or CAN RXD in the time of receiving, right? CAN TXD or CAN RXD, right? Logic 1 there is referred as recessive state, and logic 0 is termed as dominant state. Right? We'll understand why it is recessive state. Recessive state, for in case of CAN B, we CAN L is at 5 volt or around 5 volt, CAN H is at 0 volt. And in case of dominant state, these levels would change. CAN L would change to 1.4 volt and CAN H would change to 3.6 volt. So how a receiver understands that whether a bit 1 is getting communicated or bit 0 is getting communicated, how the receiver can understand? How the receiver gets this idea of whether transmitter is communicating logic 1 or communicating logic 0. How it is? So then yes, you can take the difference. The difference is 5 volt over here. And how much is the difference? 3.6 minus 1.4. So it is 2.2 volt. So it can simply find out the difference. And then if the difference is around 5 volt or close to 5 volt, the receiver can understand that 1 is getting transmitted. And if the difference is lesser than this, below, I mean maybe 2.5 volt, around 2.2 volt, the receiver can understand that logic 0 is getting communicated. That is what is the way the receiver can understand whether transmitter has transmitted logic 1 or logic 0. Right? Similarly, I mean, in case, I mean, you can just look at this diagram. This is corresponding to this. We have this diagram over here, where this is the bit 1. The CAN L is at 5 volt. At 5 volt in this period, in this window over here, CAN L is at 5 volt. CAN H is at 0 volt, and you can see that bit 1 is getting transmitted, which is referred as recessive bit. And in case of in this next time window, we have dominant bit where CAN L is at 3.6 volt, CAN H is at 1.4 volt. So this is the way the communication happens on the bus, right? This is, and then the receiver is supposed to, I mean, measure the difference between CAN L and CAN H, and then will then decode whether the transmitter has transmitted logic 1 or logic 0. This is with respect to CAN B. Now I'll go quickly with respect to CAN C. CAN C is a high-speed CAN where CAN H and CAN L in case of logic 1 are at same level 2.5 volt. So difference is 0 volt. And for dominant state, CAN H is at 3.5 volt and CAN L is at 1.5 volt. So the difference is 2 volt. So this is, I mean, we can think that this is a kind of eye, open eye. So eye is open when the dominant bit is sent. Eye is closed. We can have resemblance with eye, right? So when the eye is closed, it means that it is recessive bit. When eye is open, it means that dominant bit. So this is the way you can remember, understand, and then it is the receiver's task to measure the difference between what is getting communicated, and it will then understand that whether transmitter has sent logic 1 or logic 0. Okay, so this is the way multiple nodes can be connected to the bus, and the importance is we do require these terminating resistors, right? So as to avoid this reflections, to avoid reflections on this bus, right, we require this terminating resistors which are of, I mean, sizes 120 ohms. So it avoids then reflection so that communication can reliably happen over this, and there is, I mean, no interference of reflected energy back to this bus. So this is the way the devices are connected and communication happens, right? So thing is for CAN bus length. So this is regarding, I mean, the bus length. So the CAN can communicate at this rate 1 Mbps if the bus length is shorter. And as bus length increases, you can read on the screen, maybe as bus length becomes 1000 meter means 1 kilometer, guys, the bit rates are 40 kilobits per second. Right? The thing is, try and understand that as the bus length increases, the speed is supposed to decrease. Right? So speed decreases. right? And we do require this 120 ohm resistor to avoid reflections. So that is how the devices and ECUs are connected, and ECUs can communicate with each other. So I'm thinking is, unless and until we understand these protocol layers, it is difficult to understand and develop applications using CAN bus. So we have this in case of, CAN bus, we have these four layers: the application layer, object layer, transport layer, and physical layer. Okay, so the application layer where lot many data structures are defined, we containing maybe some sensed information like tire pressure and so on, and then these data structures or information is handed over to this object layer for the purpose of communication and so on. Or object layer would hand over information to application layer, right? It is going to extract the payload and will give whatever information that it has received to application layer. Okay, and then we have this object layer, very important layer, object layer. And guys, we do require, if this communication stack is available, right, things are very easy to program and develop applications, right? So this one of the important tasks, right, of communication network is to understand all these protocols, different protocols and different layers, so that we can utilize these layers, you can utilize their functionality, and we can use it for developing applications. Okay, so this object layer, does very important task. It decides at what time the message should be sent. That is very important in case of transmitter. And then this is for transmitter. And for receiver, it is going to decide upon whether to filter the message or whether to pass on the message to application layer. So filtering task is done by this object layer. Remember that several, why this filtering is important. Once again, we'll go to the previous slide. So filtering is required because so many devices are connected. I hope that you are on slide number 15. So many devices are connected. So many, and if the devices are communicating, lot many frames are exchanged on this bus. And if a node is not interested in receiving and passing the information to application layer of all the frames, it can filter. And that is the responsibility of object layer. So that's what is object layer's functionality. And then we have transport layer. So transport layer does many things, right? The thing is the information that is passed on, right, by the application layer could be larger in size. So the thing is, it can break, it can do fragmentations and prepare the frames. So preparing frames is very important thing. That is the duty of transport layer, or extracting data from the frame and handing over to object layer, right, is the duty of transport layer. And the another important functionality is this arbitration and fault detection. This arbitration and fault detection. So arbitration is very important task which is done by this transport layer. Okay, and finally we have physical layer. So physical layer, we already have seen that the whatever incoming ones and zeros must be converted to appropriate voltages. That is the job of this physical layer. Question on this? Any question? Okay, so if there are no questions, you can unmute and ask if required. I'm audible.
No, sir.
Yes, sir, you are audible.
Okay, are there questions, guys?
No questions, sir. Thank you.
Okay, so I hope that you are getting it and you are understanding importance of this. Soon we'll be moving to Ethernet and we'll understand many different scenarios. Let me quickly go through this. CAN, right? So thing is, the in case of the major difference between CAN communication and automotive Ethernet is this addressing. So in case of CAN, it is content based addressing. So there are addresses are not assigned to ECUs. Addresses are not assigned to ECUs in case of CAN, but the thing is the ECUs can understand the information based upon the identifiers or what is referred as content based addressing, right? The thing is each message has identifier, and based upon this identifier it can understand what is the type of message. The automotive standard F1939, right, for identifying or for having correspondence between identifier and the message. What is the message? Okay, or we can have our own understanding, we can have our own identifiers defined, and we can have correspondence between what is getting transferred, right? So if we have this correspondence based upon this identifier, the devices can understand who is communicating or what is getting communicated. That can be understood, and then filtering or accepting the messages, right, which are received by ECUs can be done, right? The thing is, think of this. So think of this CAN station 1. So we have got this, the once the frame is received, selection happens, right? And only upon, I mean, filtering, it will accept or reject the frame, right? So this guy CAN station would transmit and all would, I mean, receive. The thing is, think of this CAN station 3. So selection phase happens, which is done by object layer, right? And this object layer here, it filters this, it doesn't provide to this upper layer, which is application layer. So thing is, in that way the things are happening, right? So this CAN station 1, CAN station 4, right, are programmed in such a way that whatever messages which are sent by CAN station 2 are accepted, right? But CAN station 3 is programmed in that fashion that if the message which is communicated by station 3 is filtered, right? So this is most important part that we need to understand. Okay, and then we have got arbitration. This arbitration is based upon this identifier, right? And arbitration or race for grabbing the bus is arbitration. So if there are several transmitters, this is station 1, station 2, station 3, if all wanted to transmit at the same time, if all wanted to transmit at the same time, then thing is all cannot use the bus to transmit the like frames at the same time. The thing is, then they need to arbitrate, they will compete with each other, and this competition is based upon this arbitration technique, and this is distributed arbitration. This is distributed arbitration. So what really happens is this, all the stations are supposed to transmit their identifiers, right? So thing is this, the you can understand that in the first time instance, I mean, initially the bus is idle. In the first time instance, all transmit 0, right? Simultaneously they will also receive, right? So the station 1 knows that it has transmitted 0 and it is received 0, right? Remember that this operation is what is mentioned over here, logical and operation, right? So whenever all transmit 0, the operation is logical and of 0 and 0 and 0 is 0, and they will receive, right? And this is the status on bus line, this is that logical and, this is the logical and. So 0 and 0 and 0 is 0. So, and both all will receive 0. So they will understand that they are owner of the bus. All three at this time will understand that they are owner of the bus, right? At the next time instant, all will transmit 1, and the bus, the status on the bus is 1. So they will understand that all, I mean, these three are owner of the bus. But the next time instant, right, this station 1 is transmitting 1, but station 2 and station 3 are transmitting 0 0. So and is 0. So once and is 0, station 1 knows that it is, I mean, the some other stations are driving the bus, so it removes the line, it removes it, I mean, refrains from driving the line, it stops driving the line. So the in that case it is written as station 1 loses the arbitration here. Similarly, maybe I'll go directly over here. So thing is, station 2 has transmitted 0, and station, now there is competition between station 2 and station 3 only. So station 2 is transmitting 0, station 3 is transmitting 1, and operation is 0. Station 3 knows that it has lost the arbitration, and then station 2 would continue, gains the bus, and would continue to transmit, which is written over here. You must have read it. So this is what is arbitration, and things happens in this manner, right? The thing is, some figures which are important over here. So can mean 2a can miss 130 bit times. Thing is, this is the maximum priority message. Only have to wait for. The thing is, the remember that this priority which is given to ECUs is based upon identifiers. Okay, and for maximum priority message, the devices need to wait for only 130 or 150 bit times, and this 130 or 120 bit times at 500 kbps comes out to be 260 microseconds or 300 microseconds. Okay, so highest priority ECUs need to wait for, maybe say, I mean in case of 150, I mean bit times, 300 microseconds. Okay, so that is the latency in case of CAN. Okay, and this is the frame. This is a mechanical thing. I mean very quickly go through this, where we have this idle. We have start of the frame indicated by 1, right? And there are 12 bits for arbitration, including RTR, request for transmission. There are 6 control bits, which tells, I mean, one of the important part is data length. And then there are 64 maximum number of bits, 64 bits or 8 bytes. So this payload is very small like this. And then we have this CRC field for error detection. And we have acknowledgement, and then end of the frame. And we have this interframe space for different devices to transmit. So they wait for this 3-bit time. Okay, so thing is, and this is mechanical thing. You can go through the any standard book for to understand this. I'll quickly go through this. So we have this start of the frame, arbitration field, which is identifier, the control field, right? Very important part of the control field is the 4 bits are there are 4 bits which are going to tell how many bits are there in the payload. Okay, and what we have is we have data field where actual payload is, and we have CRC field, and we have acknowledgement field. Okay, I'll be uploading these slides on your, I'll be handing over these slides to the organizers, and you'll get these slides. In the interest of time, let us keep and let us go ahead. Okay, and we are end of the frame and interframe space. Okay, so this interframe space is needed for this only data and remote frames. So if transmitters are transmitting data frames, or if there's a request for remote frame, then this interframe space is required. For error frame or overload frame, it can be immediately sent. They need not wait for 3-bit time. So these are small nitty-gritties in this CAN communication, which one has to understand and then program it accordingly. Okay, so this is what is CAN, and then I mean what you can do is you can take any standard board. So any standard board, standard board maybe from ST Microelectronics, right? For example, one board I know is which is STM32F429ZI, and then you can go for this. This board is called a Nucleo 144 board. So this is Nucleo 144 board. You can take this where there are 2 CAN controllers available. You need external bus transceivers, which is physical layer. So once we have this board and transceivers, we are ready for programming. And then there is what is called as HAL layer, hardware abstraction layer. So lot many APIs are available, and lot many standard template codes are available. And you can use this template codes, and you can really program, and you can inspect various aspects of this CAN communication, right? So that this is what is CAN, and I try to in this whatever 20 minutes, 20 to 25 minutes, try to cover what is CAN. We'll immediately move on to Automotive Ethernet to understand its importance, because it is upcoming and very important to understand why it is taking place of standard communication buses. Right? Before moving to Automotive Ethernet, is there any question you have? So if there is no question,
Sir,
yeah,
actually,
okay,
if
yes, go
there
ahead.
is a delay, it is produced while transmission.
Delay is produced in while transmission, in the sense, remember that the speed is 500 kbps, right? So this, from this 500 kbps, what can be said about? We can find out bit time or bit interval. How much is bit interval from this 500 kbps? You're talking of this latency, right?
Yes, sir. Yes, sir.
Yeah, you're talking of this latency, right? So thing is, it is said that 150 bit time or 130 bit time, right? So when is that scenario? Let's think of 500 kbps. So how much is the bit time? 1 upon 500 kbps, right? Is the bit time.
Yes, sir.
And thing is, let's assume that one CAN communication is happening. One ECU has grabbed the bus, and higher priority, ECU is coming up next immediately. Once the bus is grabbed by one transmitter, then higher priority has to wait for one frame, and this one frame size is 130 bits or 150 bits in case of CAN 2.0b, right? The thing is, which amounts at this rate, this amounts to 260 microseconds, right? So this is a bit interval is 2 microsecond. So 2 into 130 is 260, or 2 into 150 is 300. So that is what is bit interval, and that much is the latency. For this is for what? This is for highest priority node, right?
Yes, sir. Fine, sir.
Yeah. Okay. So let's move on to this Automotive Ethernet, the upcoming technology, which is nowadays getting used in automotives or vehicles. Okay. The thing is, why this is been introduced, right? We'll shortly, wherever you see AE, it means that it is Automotive Ethernet, right? So it is especially used because of introduction of so many features in ADAS, right? Which are adaptive cruise control or active lane departure system and lane cutting, right? If you want to detect it and prevent it or give warning to the driver, right? We do require, faster speed, right? Or automatic parking system, and many, many more, right? So thing is, all these applications, right? Maybe obstacle detection, cruise control, and so on, do require larger bandwidth. And automotive Ethernet, or especially Ethernet, is the main player which is supposed to support this higher bandwidth for today's application. And maybe in future, many cameras, we'll soon see how many cameras are connected and how applications are bandwidth savvy or requires larger bandwidth. That's why people are shifting towards Automotive Ethernet. And there are other reasons also which we'll see, right? So what used to happen is this, in vehicle networks which we had seen like CAN or LIN or FlexRay or MOST and so on, they have been developed and implemented separately. So CAN was there, and in case of consumers, applications, we have this Ethernet. Maybe think of Wi-Fi or think of LANs and so on. We have Ethernet dominated networks, right? So maybe in the residence or at residence, offices, data centers, we have Ethernet. And in case of vehicles, we had CANs and LINs and MOST and FlexRays and other kind of buses which are developed. The thing is, what is happened, what has happened, what things, what magic had happened, so that now this auto or ethernet is becoming part of the vehicle. That is very interesting. We'll understand that, and then we quickly go through ethernet, right? The thing is, the main reason for separation of these two buses and infrastructure which is used for communication is, what is important is this: requirements in automotive networking are very, very stringent. Safety requirements and other requirements, reliable communication requirements are different, right, as compared to this application, normal applications at data centers or offices and so on, right? So because of this difference and the especially noisy environment, right, hazardous environment or noisy environment, right, which normal ethernet could not sustain, right? That is why the development happened differently. But what happened is, thing is, this is the past is written over here. You can see that these are data centers or lands which are connected. So this is the scenario in offices or organizations and so on. And in case of network, we have CAN and so on, right? So it was in isolation. But what has happened is, there is lot of transformation has happened, and mobile communication is now being heavily used, right, by consumers, and many features are added to CAN, right? So remember that, because of this, this both of these developments are getting now converged, right, which requires larger and larger bandwidth, right? The thing is, that is the reason why now ethernet is now base kind of technology for communication. It might be wireless ethernet in this scenario, right? It may be wired ethernet in case of car scenario, but the technology which is underlying technology for communication in both of these scenarios, right, or the future will be ethernet, right? So that is what is happening, or that is what is happened, right? Where this many features are getting added to this vehicle, which requires larger bandwidth, lower latencies and so on, right? And plus added features which are maybe V2V, vehicle to vehicle communication, V2X, right, or V2I, right? So these applications are coming up, right, which requires technology, which requires applications, which requires communication stack, which do require underlying technology as ethernet, which we will see, right? The thing is, what has happened is this ethernet, once we have ethernet in place, we have got large number of applications available, because ethernet is a 40 years old technology. So from 40 years we are using ethernet, developing applications using ethernet. Some of the popular applications are listed here: email and so on, www, file transfer, just few applications, right? Applications like audio video bridging, for streaming audio, for streaming video, ethernet is being used, right? And there are many other protocols for address resolution, right, tracing, synchronization and so on, right? So lot many applications are available once underlying technology is ethernet, and all these applications can be made available inside vehicle or in a vehicle, which is the requirement of, maybe think of navigation, right? Can we now simply move aside or neglect navigation? Certainly not, right? The thing is, navigation is very important feature of any vehicle, which we cannot separate it out, right? This is being feasible because of stack which is available, and the stack which runs on ethernet or wireless ethernet, right, communicating with infrastructure, or using 4G or 5G, communicating with infrastructure, right, makes this navigation available, right? The thing is, there are all these protocols, suite applications, utilities are designed to run on any type of ethernet, regardless of its low level implementation, right? And remember that these applications are very well tested, right? There are so many applications which are available, which are very well tested. And very important thing is these most of these are open standards, and lot of human beings or human resources involved in developing, testing these applications, right? So that's why many applications are available, and we can now thus using this technology, we can think of cars, right, where advanced audio video streaming functionality, cars which are talking to toll booths, right, cars which are having intelligent charging system, right, and many other advances in case of EVs in this case, right? That is why people are shifting towards this Ethernet, right? So thing is, one of such implementation which was available in around 2015 or 16 is this broader reach, broad R reach or broader reach, right? Who have come up with this one twisted pair 100 Mbps Ethernet, which is also referred as 1 TP, one twisted pair, C for 100 Ethernet, right? 100 Mbps Ethernet, right? They are also coming up with this reduced twisted pair gigabit Ethernet, RTP gigabit Ethernet, whose speed is now 1 Gbps, right? And because of availability of such technology in the car, right, what we can have is we can have lower cost, better integrated radar and video system, right? So thing is, these are driver assistance systems, right, which can tell us about lane departure or possible forward collision, right, by having obstacle detection, right, by mounting several cameras at the front of the vehicle, on the sides of the vehicle, right, it is possible to detect obstacles and then maybe applying brakes automatically, right? So that is what is facilitated by having such applications, right? Or we can have faster or improved stability control. Day by day the vehicle speed is getting improved, right? So thing is, we can have such system implemented in case of even maybe vehicle, right, in preventing vehicle from losing traction, right, the lane on the road, right, even in case of adverse weather conditions, right? We can have this video system that is going to monitor driver itself, and if the driver falls asleep, we can have warnings getting generated or some alarm getting generated so that driver wakes up in case he tends to sleep and so on, right? And then we can have several cameras which are installed, right? And then we can have this real time capture of video and having to a central system, right, which will help the driver driving the car safely, right? So for safety applications and so on, so lot many features are getting incorporated in the car, which are bandwidth savvy applications, and that is why it has triggered the requirement of automotive Ethernet, right? So think this is the chronology where this Ethernet has gone up to 100 Gbps in 2010, right? And in case of this vehicles, it is getting, this 1 Gbps was available in 2017. So it is being practiced now in some of the high-end cars. And this is the chronology where this wireless, technology has improved, right? So thing is, this is that chart. So as the time has progressed, we have increasing bandwidth supported by this Ethernet technology, right? Some of the features that we'll quickly go through, and we'll try to understand how to develop applications using this Ethernet. What is the stack, network stack, which is part of communication? So thing is, it is full duplex, packet switched, and address based networking. This is what is Ethernet. So we can have this switch. Nowadays, it's a star topology. So we have this switch. These are 4 ports: port 1, port 2, port 3, and port 4. Where the port 4 over here, where the devices are connected. We have display connected, console connected, speaker connected, head unit connected, right? Which has got radio communication, DVD player, or navigation, and so on, right? And then we can have this to and fro communication between, let's say, these two devices, right, via the switch, right, at the same time. That is what is full duplex, right? And to and fro communication between these two devices at the same time, right? So this is what is full duplex. Packet switching is, thing is, these packets are formed, small packets are formed, and multiple devices can send packets on these buses. That is what is packet switching. And these packets will arrive at the switch, and based upon the address over here, destination address, the packets will be forwarded to appropriate port. That is what is packet switching. And finally, we have this address based networking, which is a very important part. And let's understand how it, relieves the programmers, how it makes life of the programmers simple. The thing is, based upon these addresses, the packet will be forwarded by the switch, right? And most of the time, what happens is the gateways, this is the gateway which is supposed to implement packet forwarding, right, are implemented in software, right? So if the network topology is altered, so topology in the sense, if many devices are connected like this, that is what is meant by altering topology. So we need to make appropriate changes in the software in case gateways are implemented in software, right? But the Ethernet makes this life very simple, right? So thing is, if let's say this is the original network, if many other devices are added, we can add switches, and these switches transparently will learn the paths. The Ethernet switches transparently or automatically will learn the paths and will forward the packets. No requirement of changing the software, right? So that is the added advantage of this address-based networking, right? That is why this is very, very important, and this is gaining popularity and foreseeing its usage in, vehicles, right? So this is, as I said, this is the kind of, structure that is available. So thing is, what in vehicles we have different domains, they call, we have infotainment domain, we have powertrain domain, where there is engine, and which is supposed to drive the vehicle on the road. That is what is called as powertrain. We have body, domain, we have safety domain, and so on, and several devices which are there, and several requirements in these domains are connected using, maybe in this case it's infotainment. So it's a bandwidth savvy application which might require one, twisted pair with 100 mbps switch, right? So engine might be connected to different system, different ECUs in engine, right, where we have fuel system, alternator, transmission, and so on, by using CAN flexible data rate bus, right? We have CAN B bus connected in body, domain, right? And then further it can use LIN and so on, right? And in safety, we have this once again Ethernet, and then later on, here one can have CAN C, right? And these devices over here will act as a gateway between, whatever frames which are communicated, which if required to be forwarded to other ECUs or to the central gateway. And the central gateway will have a tap over here, right? So we can have, debug over this, or diagnostic over IP by tapping into central gateway. So your backbone is gateway Ethernet. Most of the places where we require bandwidth, we have Ethernet. And if, bandwidth is not that requirement, but if there is, some time sensitive networks, we can have this other versions. So all will coexist at now. Slowly, all these might be replaced by using, or make, sustain, or might replace in future by using this or Ethernet technology. Any question on this? We have last 15 minutes, so we'll try to cover the, how the applications can be implemented by using uh, this layered approach, right? Other features is strong, this isolation. It supports isolation, so it can work in harsh electrical environment. It is possible to, very important feature, which is supposed to reduce this wires. Wires are, this weight of the wire is almost 30%, right? So this, by distributing power over Ethernet, it tends to reduce the wires, so which might be required for powering up several ECUs, and this is going to lead, I mean, Ethernet, the very important feature, high speed and low weight, only one pair. Remember, one twisted pair, right? Which is shown over here. So this is one twisted pair, right? Connecting between transmitter. This is, let's say, transmitter where we have power supply, and these are isolation, I mean, components, inductor and capacitor decoupling, I mean, components. So the power can be sent on this bus and can be received by at this end, right? And then this controller will be powered up by having power transmitted on this bus. So same wire, same cable, right? Transferring power and data to and fro, right? So that is what is the complexity of this, I mean, standard, right? So which is nowadays available, right? And we can see that this having this so these are, I mean, cameras. So we can install camera on the front, on the sides, right? And over here, and then we can have communication, the streaming, direct streaming, right, on the dashboard, right, or on the displays, which will assist driver. So we can get 360 degrees view, right, by using this Ethernet. And remember that by using Ethernet, important thing is, like, this cable weight reduces approximately by 30%, and your car becomes lighter, right? And when the once the car becomes lighter, because of having this only one twisted pair, right? Thing is, I mean, fuel efficiency goes up, and there are many other features. I mean, environment friendly and so on, right? So that is what is power of Ethernet, right? So thing is, why this is very important slide. So nowadays, I mean, we have this wireless functionality where we have this vehicle to vehicle communication, vehicle to infrastructure communication, intelligent transport system initiatives, right? This all is possible because of having Ethernet or some form of Ethernet or Wi-Fi, or maybe communication or connectivity with infrastructure which is available in the form of 4G or 5G, right? So thing is, that is what is the importance of this Ethernet, right? The thing is all this, and then vehicle to vehicle we can have, I mean, ad hoc network formed by vehicle to vehicle, and then data gathered from other vehicles. So from this we know that what is the location of other vehicle, at what speed that vehicle is approaching, and then very important, I mean, thing is this safety, or this accidents happening on the road because of non visibility can be, I mean, eliminated or prohibited by having this vehicle to vehicle communication. So which is very important, that's why this topic is very important, that's why this adoption is big increasing, right? So I mean, we'll quickly go through this Ethernet and we'll quickly understand this, the layered approach. So the Ethernet, thing is, this is encoding, as I said, line encoding and signaling, right? So this has been promoted by open is short form for one pair Ethernet, one pair, OP Ethernet, EN Ethernet, right? So it uses only one pair, right? So this is, I mean, open alliance, right? Open alliance broad R reach, OABR, also called as OABR, right? So where we have this 100 Mbps data rate, right? Which is, you, I mean, encoded by using in three levels: +1 volt, 0 volt, -1 volt. This is going to reduce the speed, right? The signaling, these are symbols. It is going to reduce the symbol, I mean, speed, which becomes, when it is 100 Mbps, megabits per second, the signaling rate is 66 megabaud, right? So the thing is, this 66 million times only, right, the signals will be sent instead of 100 bits, 100 million times, right? And then later on, this, I mean, these signals or these symbols, +1 volt or 0 volt or -volt, is sent once again by using differential signaling, right, over a single UTP copper wire, right? So single UTP copper wire supporting simultaneous communication from both the sides, right? This is what is the complexity in this Broadcom's broad R reach technology, which is now getting deployed in vehicles, right? So this is what is this single wire, single pair. This is single pair, single twisted pair, right? 100 Mbps from this side to this side, right to left and left to right, right? And this is, I mean, possible because of this sophisticated digital signal processing technology or techniques, right? So thing is, I mean, if there are only two devices, one can have connection like this. If there are many devices, we do require a switch, right? So we have a star topology. So whatever that was shown earlier was a star topology, right? The thing is, by, I mean, we can, I mean, if there are ports are available, we can add ECUs. If the ports are not available, we can have star of stars, hierarchy of switches. So we can have hierarchy of switches and we can have star of stars, and then have network formed, and then have communication, right? The thing is, ECU in automotive industry, ECUs are routinely added or removed. Okay, thing is, there are several versions of the car, lower end, mid level, higher end, and so on, wherein the discrimination between these cars is in terms of these ECUs. How many ECUs are there? Which features are available? Which are not available? That is, I mean, really based upon whether ECUs are getting added or removed, right? And this technology or this technique, right, AC Ethernet technology, do support this addition of ECUs or deletion of ECUs, right? So thing is, uh, that is what is important thing, and that is what is driving this development, right? So in the interest of time, I'll hand over these things. This is really frame format is really mechanical thing. You can go through this, right? I lost, I mean, 5 to 10 minutes, which I want to cover the remaining thing, right? One thing that I would like to tell you is this media access control. How many of you heard this CSMACD, carrier sense multiple access with collision detection, which is not really a requirement in case of star topology with switches, having switches connecting, interconnecting several ECUs, right? Because it is point to point communication and we don't require now CSMACD. So this MAC layer, medium access control, is not really required in modern Ethernet networks. Okay. And I mean, this is, well, this is, there are some points of concerns where we do require switches, requirement of switches, and number of ports. I'll briefly tell in the interest of time. Number of ports available on the switches is a point of concern, right? The thing is, I mean, at the design time, it is very, very difficult to, I mean, select a switch with a number of ports, because, I mean, as I mean, we have several versions of vehicles, the ECUs are added or removed. So a priori, it is very, very challenging to decide switches, number of ports available. That is a point of concern in case of Ethernet, right? And the thing is, I mean, in case of bus, we can have, in case of CAN, we can have something like vehicle spy, which will sit on the bus and can capture all the, I mean, frames. But in case of Ethernet, we do require a test access port or a debug port where all the frames are available, all the frame, this frame port mirroring feature is required. So where the, whenever the communication is happening between a pair of devices, the switch is going to throw the frames on the debug ports for understanding the communication and then diagnosing the faults. So that is a point of concern in case of Ethernet. And last couple of minutes that we'll invest is on this TCP/IP network protocol, where this TCP/IP, there are two important protocols: Internet Protocol and Transmission Control Protocol. So this Internet Protocol is responsible for host to host delivery. Host to host delivery. So where, what is host? Host is any device on the network, any device on the network to which IP address is assigned. IP address is a unique address. IP address is some address which is a unique, right? So that is a host. And for delivery of packets between hosts, this layer is important. And this transmission control protocol is like delivery from one process So process to process delivery, or in other words, application to application delivery is the duty of this transmission control protocol. So what is the process? Process is one application running on this host. So there could be number of applications running on the host, and delivery between process to process is the requirement, and the reliable delivery, reliable data transfer, right, is the job of this transmission control protocol. Will not go into the history of this, will not go to the history of this. Thing is, what happened is, in around 1980, right, when TCP version 3 was going on, right, they found out that we need to break this TCP, which was called as transmission control program initially, right. So this was divided into two parts, which is IP and TCP. So that's why we directly have IP version 4, right. And I mean, what are important features? This is this integrated addressing scheme. So just now we have discussed, we have IP address, we have port numbers and so on, which are responsible for delivery of packets, right? Or I mean, information from one process to other, right? And these IP address and port number are inherently, they have feature of routing. So appropriately, depending upon destination address, the packets are routed. And thing is, this TCP/IP underlying network could be anything. It could be Ethernet or PPP or SLIP and so on. It doesn't really matter whether underlying network is Ethernet or some other technology, right? It is scalable. The thing is, this has proved this, all these hosts which are there in the world are connected using this TCP/IP, right? Obviously, it is open standard, so many developers are contributing in the development process, and it is universal now. TCP/IP is available everywhere, right? Everywhere, right? Even in telephone switching, right? So thing is, I mean, we'll skip this slide, and which we have discussed. That's why I'll skip this slide. So thing is, this TCP/IP, TCP/IP supports applications. For example, this World Wide Web is an application, right? So at application, there are application layer protocols. So this World Wide Web uses HTTP, which in turn uses TCP/IP, especially TCP, and TCP is based upon IP, right? The thing is, all these applications, remember, right, the upcoming applications, vehicle to vehicle communication, right, are, I mean, these applications are there at application layer. Underlying, they'll be using either TCP/IP or some equivalent of TCP/IP, right? So that is what is important thing, and all these applications are now feasible because of having this TCP/IP, right? So thing is, I mean, one such application is given over here, where if we have, I mean, this network, this internet, and then this LAN over here and this LAN over here, where there is a server on this other side of LAN, and there's a client over here, right? So client can communicate, right? And one, if like client wanted some resources on this server, all the way this routing happens, right, between this switch and then outgoing switch, this external router, and then routers over here, and then routers, and then the packets are received by the server and then transmitted back, right? So this inherently, this is taken care by especially IP, this host to host delivery, and then the whatever the process which is running at this client end and server end, that is been taken care by TCP, right? So because of this, right, it is possible, and because of having Ethernet and because of having layering like TCP/IP, we have lots of applications getting developed, and that is going to give us, I mean, uh, a lot of, I mean, applications, lot of features in the car, right? So thing is, and the thing is, the model that is used is client server architecture, client server programming, right? Will not, in the interest of time, will not go through this, right? The thing is, this client server architecture, we have servers, we have hardwares, we have softwares, and we have transactional rules, where one thing that I would like to, I mean, mention over here is, client is supposed to initiate the, I mean, communication or sends a query, and server is going to respond to this requested, I mean, query. That is what is client server. So server is up and running, client is supposed to send query, right? And some examples are given over here. I mean, go through the examples and try to understand, right? We'll try to conclude, we'll try to I mean, I think is there's a reference. There is one-to-one correspondence between this OSI layer and TCP/IP layer, where this layer number 1 to 4 there is equivalent in TCP/IP, and this session layer, presentation layer, and application layer all combined in this. I mean, applications that uses TCP/IP network, right? So below is TCP/IP. This is TCP/IP, and then all these layers, the functionality over here is in embedded in application layer. And finally, I mean, I would like to show you this slide. That is, this all these layers. I mean, layer 2, layer 3, 4, 5, 6, 7. These applications are, let's say, application like, let's say, think of DHCP, or let's say TFTP or HTTP, have got this implementation of layer 5, which is session layer, presentation layer, and application layer. And then, I mean, at this layer 4, we either have these two celebrated protocols, which is TCP or UDP. And then at layer number 3, we have this IP. And along with IP, there are so many protocols, especially this fraud routing. We have so many host of protocols, lot many protocols. And then here we have automotive Ethernet. At layer number 2, we have Ethernet, right? So this is what is the layered approach, right? The thing is, for this is a very important slide. You can go through these references to understand CAN and other protocols, LIN, and so on. To understand automotive Ethernet, you can go through this reference, which is the definitive guide by Charles, and these authors. I'm not, I mean, utter this. For implementation, we can go through this. This is lightweight IP protocol stack, LWIP stack. So you can really implement all this and understand these implementations. Right. So thing is, like to conclude, so I would like to thank organizers, and if there are any questions, I'm ready to take up, let's say, a couple of questions. If not, I'll hand over these slides to the organizers. Can go through these slides. Try to. This is just, I mean, we cannot, I mean, understand everything from, let's say, 1.5 hour lecture. So you need to put in efforts to understand this and to grow up. That is my request to you. So where these references are available, you can download the references, or the part of the references are available, or you can procure and you can study. So I would like to stop here and wait for a few questions. If the organizers have collected questions on the chat, or if someone wanted to ask questions orally, I'll take it. Otherwise, we can stop here. Yeah. Mostly, sir. Are there questions?
Will CAN completely replaced by Ethernet in future vehicles?
Yeah, so that is the aim. That CAN and LIN and other protocols, other bus standards will be replaced by automotive Ethernet, where, I mean, efforts are being made for very high speed automotive Ethernet. And remember that at physical layer, there are a lot many challenges. Upper layers are well established. So a lot of things are happening at physical layer. As I said, I mean, in case of noisy environments, for reliable communication at high speed, there are challenges. Yes. Any other query? So if there is, are there organizers available? Organizers are there?
Yes, sir. Yes, sir.
Yeah. Okay.
Uh,
I'll stop
so
sharing.
yes, sir. Anybody has question? Okay.
No, sir. Thank
Okay.
you.
I think it is understood by
It
everyone.
they will
So,
understand afterwards. Yeah. Okay.
dear sir, I would like to extend my heartfelt gratitude for taking the time to share your expertise on automotive communication network, traditional CAN versus automotive Ethernet. Your insightful presentation and engaging discussions have greatly enhanced our understanding of these critical topics in the automobile industry. So, thank you again for your valuable contribution to this ATAL FDP.
Thank you.
Thank you,
Thank you
sir.
so much. It's my pleasure to discuss with you and contribute in some manner. And I'll send the slides to you on WhatsApp.
Yes, sir. Yes, sir.
Okay, and you can pass on.
Yes, sir. Yes.
Thanks.
Okay, thank you. Now our next resource person, Dr. Deeplaxmi Niture, ma'am.
She has joined.
Ma'am, are you there?
Yes, sir.
Okay, okay. All the best. Nisra madam, bye.
Yes, sir. Bye, sir.
Just ma'am, 1 minute.
Yeah.
I will
Am
make
I
you.
clearly audible?
Yes, ma'am, you are audible.
Okay.
Let me have your short introduction. Dr. Deeplaxmi Nithore ma'am hold BTech and MTech from the Electronics and Telecommunication Engineering Department of Batu Lonere. She completed her PhD in the same field of Savitribai Phule Pune University in the year 2021, and currently she is an assistant professor at the Department of Electronics and Telecommunication Engineering with over 14 years of experience in the teaching and academia. Niture ma'am has authored numerous research papers published in peer-reviewed journals and presented at a leading conferences. Her research interests are diverse, encompassing ultra-wideband antennas, reconfigurable antennas, electromagnetics, RF and microwave communication, and Internet of Things, as well as quantum computing. She is actively involved in the cutting-edge research through her affiliation with the Center of Excellence in Advanced Electronics Manufacturing at COEP Technological University and Center for Design and Application of IoT at Research Park, Chikli Campus, COEP Technological University, Pune. So with this, I welcome Dr. Niture ma'am to take the charge and start your session.
Thank you, sir. Just I will share my screen. It not enabled, sir. Please enable the screen sharing.
Just a minute, just a minute. Ma'am, please check it.
Okay.
Yes, ma'am, it is clearly visible.
Okay, fine. So just check once whether it is going in slideshow mode or not. Yeah.
No, it
Is
is
it?
not. It is not in slide show mode.
But from my side, it is in slideshow. And check whether the slides are scrolling
Yes,
or not.
slides are clearly visible. No problem.
But I have I have gone to the next slide. Whether it is moving, still on the first title slide.
This is in the
It
first
is
slide
a
only, madam.
first slide, first slide.
It's not moving. Just let me check.
You just press F5 on your keyboard. Yes, yes. Now it is.
A message popped up that screen sharing has stopped. Okay, okay. Just a minute. Just a minute. I will do it again. F5. Now, is it visible?
Yes, ma'am, it is visible.
Hello?
Yes, ma'am, it is visible, but not in PPT mode.
Hello?
Slideshow mode is not activated. You have to activate that slideshow mode by pressing F5 on your keyboard.
Yeah, done, but I think it's not going.
Okay, ma'am, it's visible. You can start. No issue.
Okay, fine. Okay, sir. So first of all, I would express my sincere gratitudes to Dr. Mukane, Principal Shivnagar Vidya Prakashan Mandal's College of Engineering, Malegaon, and Professor Kale, and the entire organizing team for inviting me for this expert talk on quantum computing and secure communication. So I will try to explain whatever I could learn over these years and try to put this topic in a simple manner, in a very easy manner, because when we actually go into quantum computing or cryptography, a lot of mathematics definitely will be involved in it. So here the topic given to me is quantum computing and secure communication, which has two big topics combined in a single one. One is quantum computing and the other one is a next generation communication. So I tried to put these two topics uh, in a single presentation and kept it as light as possible. Hope all of you will be me and uh, listen me patiently. So to start with, uh, as I said, the topic is quantum computing and secure communication. So I started with the presentation outline would be the I will give you the brief introduction to evolution and brief overview of the next generation communication. See why I started with this the overview of next generation communication, because as I said, now what is the exactly why do we need the quantum computing in implementation of the next generation communication? What exactly the need of quantum computing for next generation? To understand that thing, we need to first understand what is the uh, this next generation communication, that is 5G, and the anticipating 6G communication. So whenever we look around, we see that communication is evolving at an exponential rate, from introduction of 4G network to upcoming 5G networks, and then anticipation of the 6G and beyond. And the way we connect, share, and interact, that is becoming very faster, more reliable, and more ubiquitous. So communication technologies are at the heart of everything, we can say, from self-driving cars, remote surgeries, to smart cities and artificial intelligence. But with what speed these technologies are advancing, the same speed, the complexity of the data, that means complexity of securing the massive amount of data is also increasing. So today's topic is something related to this. It is all about ensuring that this communication, how we can make this data secure, or how we can make this communication secure. So it is all about ensuring that these communication are not only swift, efficient, but at the same time, how we can make them safe and private. Now, uh, while we are evolving into a new era of next generation communication systems, the security infrastructure of our current networks may soon be outdated, because with this quantum computing, or maybe the uh, attacks, uh, the threats, the uh, security may be at the risk. And to cope up with this, we need a sophisticated algorithms or sophisticated things to make the security foolproof. And here the quantum computing steps in. As this quantum technology matures, it promises to offer an unprecedented level of computational power and new paradigm for the encryption that could safeguard the future of communication networks. And at the same time, this quantum computing also means it is safeguarding. At the same time, it is also uh, uh, introducing some new risk to break the very encryption protocols that secure our current communication systems. So we step into So as we step into the future of next generation communication system with 5G and 6G, and obviously the Internet of Things, which is transforming the landscape, how we can use this quantum communication, or sorry, quantum computing, to build a secure system for this new era, and how do we protect our future communication networks from the same quantum computing technologies that could disturb them. So that's why uh, the topic or outline is based on that thought process. So we just quickly go through the evolution of, because I'm talking next, when we talk about the next generation, we think about the 5G and 6G and beyond. And the evolution, to understand this 5G, 6G, we must understand their earlier versions, that is 1G, 2G, 3G, 4G, and like that. So, and then how we can use this quantum computing to make the next generation communication secure. Then further, the topics covered are the basics of quantum computing, like fundamentals like superposition, entanglement, then the qubits, gates, quantum circuits, those all fundamentals, and then a few, just a brief introduction to the quantum algorithms and what are the available quantum cryptography and what are the post quantum cryptography and what is the difference between those two. And I will just listed few of the open source quantum simulators using which we can simulate different quantum scenarios. And next is challenges and future outlook for the same. So with this outline, I will start my presentation. So hope the slides are clearly visible to all of you. Uh, as it is not in slideshow mode, I don't know whether
Yes, yes,
the
yes.
contents are okay.
Yes, ma'am, it is in slideshow mode.
Okay. Okay, fine, sir. Thank you. So going further, so on this slide, this slide, the few slides best for the communication, 5G and 6G, all this evolution slides that I have taken from the Department of Technology, Government of India site. So even those are cited over there. This particular slide, which displays the evolution of 5G from 1G. So what we can observe here is that the 1G, that is the first generation of mobile communication, this one. So it is started in early 80s, and the lot at that time a lot of technologies were rolled out to implement this 1G. Now say why number of, because each and every country or region were trying to set up their own networks. So for example, the USA, they have their own technology called as a uh, AMPS, which stands for Advanced Mobile Phone Service. Then the Nordic countries, they had their own, which is called as the NMT, that is Nordic Mobile Telephony, and the other, like Japan and other European countries, they were having TACS, that is Total Access Communication System. So basically, these means different countries or different region had their own mobile technologies, but sorry, I think, hello.
Please check, ma'am, what happens.
Yeah, it was
Yes, yes,
automatically
it's okay.
getting
Okay, okay.
disconnected. I don't know what's the reason. Okay, so as I was talking about the first generation. So first generation, basically it was mostly the related to the analog voice communication. And as I mentioned, the different there are number of technologies, each means floated by different countries or region. And then after that, 1G, and as
Ma'am,
I mentioned,
hello.
yes, sir.
One request, you have to start the recording.
So the rights are with me.
Yes, with more option is there.
Yes, okay.
Just click on that and you have to start
Yeah,
the
it's
recording.
actually recording is going on
Going
because
on?
yeah, because yeah, see here, it is showing the stop here, no? So even recording is going on, and the options
Okay,
I can
okay,
see is
ma'am.
pause
If it,
recording and stop.
okay, if it is going on, it's fine.
Okay, so okay, so uh, so as I mentioned, the 1G was analog voice kind of a communication, and after that, exactly after 10 years later, the 2G was rolled out, and here the same technologies are means evolved, like the AMPS was evolved to digital AMPS, and then European ITC evolved to the standard called as a 2G or GSM global system. Now here in 2G, the digital voice was introduced. In 1G, it was analog voice, whereas in 2G, it was a digital voice was introduced. So, so in 2G launch, uh, the digital technologies were used preliminary in addition to the digital EAMS and AMPS and GSM. And also there were technologies called as IS-95, which is based on the uh, 95 IS-95 based on the CDMA, and uh, even though there were two, three technologies rolled out, the most popular or most successful technology was the GSM technology. Then after again 10 years later, the 3G technology or 3G was evolved. So in 3G, again here also we had a number of technologies like GSM, which is evolved to uh, WCDMA, and also we also sorry, GSMA evolution, and we had WCDMA, which is evolved to HSPA. HSPA stands for high speed packet access, and the HSPA plus, which is evolved high speed packet access. And from the CDMA side, it was uh, EVDO, that stands for Evolution Data Optimization, Revision 1 and Revision A and Revision B, which is so here along with means the more main focus, or here the data was introduced in the uh, mobile communication. So 1 minute, I'm getting a message that it is not in full screen. Just
Yes, ma'am, it's okay.
hmm,
No
hmm.
issue. It's in full
Okay,
screen.
okay, okay. So again, after 10 years, so as I mentioned in uh, uh, after 3G, after exactly 10 years later, 4G was rolled out. And this technology again had more than one technologies. Uh, and the technology evolution was from GSMA and WCDMA into LTE. So LTE stands for long term evolution. So we had different versions of LTE like LTE, LTE Advanced, and Gigabyte LTE. So in addition to this LTE, there is another one more technology which is called as a WiMAX. So WiMAX version 16.m was there, but that was not succeeded as LTE, and so the version, or so the technology which you could succeed in 4G is the LTEs, and now also for 4G we are using the LTE only. So in LTE, some sort of mobile broadband was introduced. Means what? Sort of mobile broadband means multimedia is introduced in the 4G itself, and after 4G means after again 10 years later, 5G was evolved. So around 2020, in India it was actually started from 2022, and the this 5G cellular technology, it is not only for the human being or not only the people, it was for even the machines also. That is the main thing about this 5G. So so smartphones are for human as well as machines, and uh, lot of new technologies came like edge, uh, then network function virtualization, slicing, and it have use cases for all sectors of economy. Now to summarize, we can say that the first evolution uh, from 1G to 5G, what we can say that the mobile technology is continuously evolving. The second is after every 10 years, the next generation of mobile technology evolves. And thirdly, every next generation has brought over 10x increase in the capacity. That is about the evolution in short. Now, let me quickly give some of the important features of each of the generation. Mm. So in 1G, the it is all about the uh, AMPS, and the spectrum band which they were using was same. There were AMPS, NMT, and uh, tax, but the slides or whatever values I have written here or whatever features discussed here are with respect to the AMPS, that is Advanced Mobile Phone Services. So it was using the spectrum band uh, of 900 megahertz, and in some countries they were using around 800 megahertz. So the bandwidth is on the lower side of the band. Uh, and the access technique used was FDMA, that is frequency division multiple access. And in hope all of you know what is FDMA, that is frequency division multiple access. Here we have smaller chunks of frequency as shown in figure, each of 30 kilohertz band, and the it is we use FDMA and frequency division multiplexing in the 1G communication. Uh, Now, so the concept of cellular or hexagonal cells were actually introduced in the 1G itself. Uh, Even though the only it was used for voice communication, analog voice communication, but the concept was introduced in 1G itself. You can see here a cell, and uh, the frequency or entire frequency band, it is divided into small chunks, and we can say that if uh, suppose here in one cell there are two channels, channel A and channel B, so which are separated by six channels in between, consecutive channels. So there could, I means, which can avoid the interference between them. So the concept of frequency reuse or concept of a cellular or hexagonal cell was introduced in 1G itself. Uh, so this is actually the Motorola phone. It was made by Martin Cooper. This is mobile phone, but it is looking like just like a cordless phone that we use today. And the main feature about this is the mobility was enabled to some extent in 1G. mobility means even though mobile user is roaming from this cell to this PTS to this, it could had a connectivity. So but the problem is, even though it could achieve a kind of mobility, it could not have a smooth hands off. Means even the 1G generation tried to have a good hands off, but it could not achieve it because in network side, if you observe, there was a connectivity to backbone connectivity to PSTN network, because most of the majority of the customers were on the landline phones, that is on the PSTN, that is public switch telephone networks. So in short, we can summarize like that. The 1G is some sort of mobile communication, or some sort of foundation of a mobile communication, because the frequency reuse concept and the cell structure things were started with the 1G. Then it was an analog technology for analog voice, and but the thing is, the voice quality was not so good, uh, being analog, and also the phone size was very large compared to today's mobile phone size. Then the problem was battery life. Then overall capacity of the system was also limited, because there uh, analog, because of the analog technology. Then reliability also was very poor, because there was no encryption used in the channel. So coming to the next one, that is 2G. So in 1G, the band size was of 30 kilohertz, the channel bandwidth. Now during 2G time, the GSM technology came, and it had a bandwidth of channel bandwidth of 200 kilohertz. So actually there was one version, that is digital AMPS, but as we discussed earlier, the GSM was the successful version, or the successful technology from 2G, which is still going on. So here the channel bandwidth is around 200 kilohertz itself, and the technology used, the multiple access technique was means along with FDMA, it also uses a time division multiple access technique. So because of that,
Hello, ma'am. Sorry to interrupt you,
hmm.
but we are observing only slide number 3. Slides are not moving.
So shall I switch to some other device, or it is problem of my laptop or on your side?
No, no. From our side, it's okay.
Maybe.
Now it's moving. You just
Ma'am,
Okay. Uh-huh.
maybe on from your laptop, you have to go for the full screen mode. There is a slideshow from the current mode.
Yeah, slideshow is available, but
From
who
the
is the
current mode. Slideshow, click on the slideshow and go for the current mode.
no? It is
now
not.
it's okay. Just click on the same icon.
No, already it is now in a slideshow mode. Okay, in a slideshow control, slide control option is there. Maybe.
Just check whether your slides are moving or not. Just check only.
No, though not moving now.
Slide.
I think I have to share the
Excuse me, ma'am.
screen.
Again.
Ma'am, if you have a PDF version, then it will be better. Sometimes a PPT gives this kind of error.
Other
So
participant, please mute your mic. Other participant, please mute your mic.
Okay. So let me stop. I think I will share the entire screen. Let us check with that. Screen. Okay. And now, is it visible?
Now it's okay. Now it's
Now-
okay.
Yes, ma'am. Yes, right.
Now
It's
it's
okay,
Okay.
ma'am. Just check whether slides are moving or not. Just
Okay.
only check.
No, those are not me. Just okay, maybe. Just
Ma'am,
hmm?
is it possible to share the slides to the Kale sir? Then Kale sir will share the screen. Send
Just
whatever be the PPT, send to the Kale sir. Then Kale sir will share the screen.
but in that case, sharing means control will
You
go
have
to
to
you.
talk.
You will say only the next slide, next slide. Then he will move.
Okay, just a minute. Okay. Just a minute, sir.
Yes, ma'am. It's okay, ma'am. Yes, now it's moving. Yes, ma'am, it is okay now. Hello, ma'am. Your voice is not audible.
Hello. Hello.
Yes, yes, yes. It is.
Okay. 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 So, in 2G, as I said, the channel bandwidth is now increased to 200 kilohertz, and we were using the combination of FDMA and TDMA in GSM. So overall capacity got increased because of that. Because see, with the use of this TDMA, we could divide the entire channel into small chunks, and on time division basis we could use them. So with that, the channel capacity has increased or doubled, we can say. And theoretically, simultaneously, uh, 8 users can use this 20 kilohertz of channel. So with the use of this combination of FDMA and TDMA in GSM, the overall capacity of this has increased. So uh, actually, because of some of the time slots used for the control signaling, so effectively there could be the less, maybe 7 or 6 time slots in one 200 kilohertz channels. So in addition to this, uh, to the same 2G evolution, uh, at the same time duration, some compression techniques were also come into existence. So as we know that our voice data uh, our voice, the data rate of our voice is around about 64 kbps, which was used in landline telephones. Now, to save the radio resources, compression was applied to the voice signal. So we call it as a voice encoding or vcode. So using the vcoders, the 64 kbps voice was encoded to 8 kbps voice, and even though we have reduced it to 8 kbps, there was no worsening in the quality of the voice. So on the air interface from BTS to the user, so from here, BTS to user, uh, there was means the quality was means it was not getting that much affected, and one time slot can offer at around, we have just seen that the one time slot of around, it can support when we divide that 200 kbps over around 8 slots, considering the control signals also, one slot can offer around 13 to 14 kbps of data rate. So we can easily accumulate this compressed 8 kbps voice data or voice signal on that. So we were able to carry the 8 kbps voice onto the one time slot. So with the use of this compression, that means addition to the combination of TDMA and FDMA, the addition of this compression has increased the overall efficiency of the 2G system. Now, the even though the concept of cellular was borrowed from 1G, the concept of frequency reuse was borrowed from 1G. The frequency reuse continued in the 2G system also. Hope the slide is moving.
Yes, ma'am. Yes, ma'am.
Now
It's
I am
okay.
on slide 8.
Yes, yes, yes.
So this slide shows the network of 2G network. So we can see here a handset. So we all know that the mobile phone must have a SIM. A SIM is some sort of a subscription. We buy it from the telecom operator. This is completely different from the CDMA system, where a phone itself will be bundled with the SIM itself, right? There is no separate SIM for the CDMA. But later on, they also added a SIM, and but we know that in GSM uh, had a separate SIM, but in some of the countries, even GSM had a bundled version. Okay, so this is about the mobile side or mobile phone. We assume that the 2G is GSM, all about GSM. So mobile phone with a SIM card inserted into it. And on the network side, when we come on to the other side, radio side, we have two components. Uh, one is a BSS, and in that, one is a base transmitter station connected to base station controller. This one through a ABIS interface. Uh, so this base station controller controls the multiple number of BTS, and then this will get connected to the core. This is a core network. So the core will consist of mobile switching center or mobile switching center, which will connect the base station controllers, and then it will connect it to the gateway mobile switching center, which will be connected to the outside PSTN network. Okay. We had another functions in the network, core network. Those are VLR. Uh, Hope all are aware of this. This home location register, HLR, and VLR is virtual location register, and then the authentication center. And so these are some of the other functionalities present on the core network. So these were the network functions. in the 2G era. So to summarize quickly, I can say that the 2G is about uh, digital voice, and it uses the digital technologies compared to the analog technologies used in 1G. And then system capacity has increased because of the 200 kilohertz channel bandwidth instead of 30 kilohertz that was used in 1G. And we can have eight time slots on the 200 kilohertz channel using the uh, voice encoder, and also using the frequency reuse concept. And we can split the cell and have more number of BTS in the same area. Now the two more features of 2G which users like, and even it was very useful to all of us, which was not present in 1G. Those two features were introduced in the 2G. The first one is a SMS facility and the other one is a mobility. So with the SMS, some data part is introduced in the cellular network. And mobility is related with uh, roaming, we can call. So even means earlier no standardization were there, but with the introduction of GSM, which is a standard based technology, so we could take a GSM based mobile and go to any other region or any other country, then too we could have a connectivity. So that is nothing but the mobility. So with the 2G generation, we had that SMS facility and mobility. So these two features, important features, were introduced by 2G. Now, uh, apart from that, we had in a 2G, we had also uh, had a means in 2G second generation itself, GPRS was introduced. So with the introduction of that GPRS, that 2G was nomenclated as or nomenclature as a 2.5G, and it is no more 2G. So so uh, so when it was in GPRS was introduced, it was 2.5G, and later on it was evolved to the age. Age is enhanced data rates for GSM evolution, and we call it as a 2.75G. So basically, through this, the multimedia was introduced in the cellular network. So talking about 2.5G and 2.75G, the GPRS technology was introduced, which was then evolved to the edge technology in the 2G network itself. The pure 2G network was not able to support this data, and because see, the 2G was supported by this core network. Now to support the multimedia or that kind of data, the mm, the basically some changes had to be made in the core network. So uh, we had to introduce the SGNSN and GGSN. Those stands for serving GPRS support node and gateway GPRS support node, which are nothing but the which are used to support the data and call on to the 2G network. And of course, other software upgrades has to be made to the network into the that is nothing but into the BTS, BSCs and MSCs, which can be or which could have been done from the core network itself in the 2G. So coming through the 3G, so in a 3G, we can observe that now the channel bandwidth has increased to 5 megahertz. Earlier 1G it was 30 kilohertz, 2G 200 kilohertz, now 3G 5 megahertz. So channel bandwidth has increased. That means capacity, channel capacity has increased, and it is almost 20 times bigger channel bandwidth compared to the 2G. So uh, in addition to that, CDMA kind of waveforms were also introduced here. So, wideband W stands for wideband CDMA concept was introduced here. Wide because the channel bandwidth or here is increased to 5 megahertz, so which is wider. So wide CDMA. So wideband code division multiple access was a kind of waveform which we use, and then the other name to the technology was UMTS, Universal Mobile Telephone Systems. So uh, and this was actually leveraged on the top of GSM network itself. And this technology was this generation was came around 2000, and later on this WCDMA evolved to the uh, HSPA, and to the higher version with the use of higher modulation versions. Okay, so I will go somewhat quickly for this uh, 3G version, sorry, third generation, a 3GPP group take an initiative, and at the same time means when the 3G was evolved, the 3GP P was also come into existence. Uh, it is a 3GPP is a consortium of many other standards developing organization from the other countries, and this group was formed to have a single mobile standard for world, and 3G standards was the first standard which came from this 3GPP. They had also adopted the GSM technology and keep evolving, but primarily they started with the 3G onwards. So this is about okay. Okay, this is all about the modulation used with a higher modulation, how the data rate increases, and further we can increase the channel efficiency or capacity by having a carrier aggregation. With that, we can increase the channel capacity. That is the main thing behind this particular slide. So, coming to the 3G network. So here we can see that again at the mobile, and this side we have a mobile with a SIM inserted to it, and on the radio side, earlier we had in 2G we had BSS, but now that is replaced with a RAN, that is random access networks. And so here we can say that with 3G era, uh, the BTS, that is base transceiver station, is now called as a node, and the BSC, that is a base station controller, now it is called as a radio network controller. This is node. Node is analogous to BTS, and this radio network controller is similar to the base station controller. And the other basic functionality are more or less same. Uh, but there is some evolution happened here on the core side, that is core network here. uh, so uh, we have two different domain here. One is a circuit switch domain, this one, and the other one is a packet switch domain. So this is something new to the 3G, and we had a MSC, GMSC, and so on in 2G. And the same thing is carried in the 3G as well in the circuit switch domain. And so uh, this is used to carry the same uh, messages or voice things, and to transmit the IP multimedia or multimedia type of a data. Here something new thing is introduced here. with the use of IMS. IMS stands for the IP Multimedia Subsystem. So that was the new thing, and to the 3G. So quickly summarize this. 3G, it offers the digital voice and SMS, and the mobility is from 2G itself, and SMS also coming from the 2G. The new thing which came into the mobile web in the 3G is a mobile web browsing, uh, and the on radio side it was WCDMA, and ITU has suggested the speed of 384 kbps was the uh, for mobile users or the roaming or moving, or for the stationary users the speed is around 2 mbps, which was means this was the speed defined for IoT recommended or defined or suggested speed in 2G thing, but it is evolved to 7.2 mbps and then 14 in 3G, uh, and also the mobile phone started using camera in the 3G itself, and some mobile phones also allow the video calls in a local region. So it was a native video call, and GPS was also started, which provides some navigation service. That was also in the 3G time. So, 4G, the bandwidth is around 20 megahertz. Technology used is OFDM, orthogonal frequency division multiplexing, and completely new concept called as a MIMO technique, multiple input, multiple output antenna technique, was introduced, and uh, the 4G phone had 2x2 MIMO. Again, this was there to increase the capacity, and so even it has used as a carrier aggregation. So aggregated, the capacity is aggregated up to 100 megahertz for higher data rates. Keeping this because I have to cover even the quantum computing parts. So we can clearly see here in compare 3G and 4G. 4G, the main technology is LTE, and we can observe here the 3G had a core circuit and packet core, the circuit core and the packet core, but the circuit core is absent in the 4G. And so another thing about this 4G is it can already that was discussed. IMS is there present in 4G, which will support the multimedia type of a thing. And so one more thing here, the in 3G we had a backhaul compatibility or backhaul support uh, based on this T1 backhaul, that is uh, now that is replaced with a fiber optic cable. So we know that with the fiber optic cable, the backhaul compatibility uh, is provided by the fiber, which has a higher capacity compared to the T1 backhaul. And other differences, as I said, that the 4G, it is not having the circuit core, and and because of that we cannot support the voice, and to support the voice we need to have a system called as a IP multimedia system. So here the voice over LTE, that is VoLTE, was introduced, which provide the voice. So here 4G as circuit core is replaced, and the everything is now data based. Even the voice is considered as a data. So this is a data only technology, and voice is sent over a voice over LTE. It had a mobility as well as it supported the SMS services, the broadband, the bandwidth has become broader. That means it is supporting the multimedia things. It has a camera, has high speed, high data rate. The phones were smart, and mobile had different apps and social media, and with even it has a high video consumption. So these are the few features of the 4G network. So these are the few core capabilities of 4G, that it has 1 Gbps of peak data rate. That means the maximum data rate 4G can achieve. Then the user end experience data rate is around 10 Mbps. The spectrum efficiency is of 10 bps per hertz, and the latency is up to 10 millisecond. So these are the few 4G capabilities. So obviously, these are definitely more enhanced compared to the earlier version, and we are expecting more advancement in the 5G. So obviously, based on that, the ITU has defined the requirement for the 5G. So 5G is not only supporting the smartphone but also supporting the use cases in different sectors of economy, and that's why we say that this is also for machines. So fifth generation of mobile communication is some sort of generation for machine to machine communication, and also this is useful for people, businesses, society, and all. So overall, high level, we can say that 5G is a high level of system compared to its earlier version. Now this 5G has, that's why we can observe that now end user, uh, earlier generation we shown only the mobile phone as a end user, but here we can see a vehicle, a car, drone, or maybe aeroplane can be considered as a user equipment or a customer. And then uh, on radio side, now the radio is called as a next generation RAN, so which is next generation radio access network, and we also call it as simply NR. So and then NR, sorry, next generation RAN, this is new RAN, uh, and or new radio. Other terminology is to this is G node B. uh, in 4G we call it as a E node B. Now in 5G it is G node B. So we have a next generation G node B. So that's all about the radio part, and then we have a core network or core part. Uh, so similar to other cores, we have 5G core, and then we have data network. This one, in 4G it was a packet data networks. Here it is simply data network. Mm, because the 4G supports only IP type of a data, whereas this 5G used to support structured and unstructured IP, non-IP type for data. So it is a data network, but in 4G we used to call it as a packet data networks. So that is a difference between the 5G and earlier version. But 5G was supposed to uh, new kind of a network that is designed to connect virtually everyone and everything, including the machines and other objects. So the architecture of 5G, the again it is categorized into two types: the 5G reference point architecture and service point architecture. So architecture service point. Oh, sorry. This is reference point architecture. So we call it as a reference because here we call it as a reference point architecture because the network functions are connected to each other based on some reference point. See, these all are called as a network functions: access and mobile function, session management function. So these are connected to one network function, N11. So as I mentioned, we call it as a reference point architecture because the network functions are connected through some particular reference or network function. So similarly, these two are connected, the user plane function and the session management function connected through N4 network function. So uh, this network function are nothing but different protocols. Using those two uh, functions can talk to each other. This is a reference point architecture, and then we have a service based architecture. A service based because uh, here if I take any of the function that is AMF, this particular uh, function can provide certain types of services, and even it can ask the services from other networks functions. So services, it is just a service. So one network function is asking the services to others, and everyone can ask the services. So that's why it is called as a service based architecture. Okay. So we can 5G, these are about the architecture of a 5G, service based and the reference based architectures. We are not going in detail about all these things, but remember these are the connections are all the network functions are connected to each other through APIs, uh, and these interfaces are API based. Even the outside interfaces are through APIs, and we can segregate here in 5G the control plane and hard user plane. We can segregate it, through which we can segregate the hardware and software part, and now network can be deployed on virtualization on virtual basis, and here that's why the concept of network function virtualization uh, was introduced, and even we can install the things on the cloud and then access it is possible in the 5G architecture. So some of the ITU has uh, defined certain use scenarios for the 5G. These are the ITU defined scenarios for 5G. Basically, there are three, that is enhanced mobile broadband, ultra reliable low latency communication, and massive machine type of a communication. So 5G, we want it to be enhanced version of earlier generation, and that's why these three scenarios are defined by ITU for the 5G. I mean, users are expecting these kind of a services from 5G. So enhanced mobile broadband. So it is what we expect from the enhanced mobile broadband. We want the data rate to be higher. So expected data rate is 20 times larger than 4G. 4G, the data rate was 1 gigabits per second. Here it is 20, expected to be the 20 bits, 20 gigabits. Practically, this is the ideal case values. Practically, we get around 9, means the current scene I am saying, around 9 gigabits per second or something like that in downlink, and uplink it is ideally it has to be 10 gigabits per second. Similarly, the peak spectral efficiency is expected to be 30 bits per second per hertz. Downlink peak spectral efficiency, whereas uplink is 15. The user experience data rate, downlink is 10 times faster than the 4G, around 100 megabits per second, and uplink 50 megabits. And at the same time, the mobility, we want mobility to be more. That means we are expecting uh, that even we could able to use the internet or mobile services when we are traveling at a speed of 500 kilometers per hour. So that is the expectation from 5G. The mobility should be around 500 kilometers per hour. So the next scenario is 5G ultra reliable low latency communication, where we uh, want the latency to be 1 milliseconds, which is 10 times better than the 4G. Reliability, we want ultra reliable communication, and that means reliability is more reliability is expected, and the mobility interruption is 0 millisecond. So that is related with a smooth hands off. There, when we are moving from one BTS to another BTS, there should not be any lag in between. That is nothing but this mobility interruption. Then massive type of machine, massive machine type of a communication. So here this is for the uh, use cases like smart cities, remote sensors, actuators, smart homes, wearables, or where IoT kind of a things where large number of devices are connected through 5G network. So where we expect a large number of devices are connected. So connection density we want more. So we are expecting around 10 lakh devices per kilometer square. And energy efficiency, from energy efficiency point of view, the efficient data transmission is required, and the low energy consumption, because when we talk about the IoT, the devices could be in a remote area or maybe in a not reachable area. So we expect them to they and maybe those are battery operated. So we want them the battery should retain for longer time, around 10 to 15 years. So in that case, we want the low energy consumptions, and that's why we expect a low energy consumption. That is one of the criteria for 5G thing. So these are the 5G capabilities compared with the 4G, which is called as the IMTS advanced, whereas IMT 2020 is nothing but the 5G, and the same capabilities are compared here. So user experience data rate, in 4G it was 10, so in 5G we are expecting 10 times more to that. Then spectrum efficiency must be increased by threefold. The mobility should change from 350 to 500. Latency in 4G it was 10 millisecond. In 5G it is 1 millisecond. Then connection density, it should be from 10 raised to 5 to 10 raised to 6. Then network energy efficiency, it is 10 times more. Then area traffic capacity, it should also increase by to 10, and the packet data rate from 1 to 20, that means 20 times more. So same way, here this particular diagram represent the scenarios, 3 scenarios we seen now. So enhance which capabilities are more important for which scenario defined by ITU. Just for example, ultra reliable low latency communication, that there we require the mobility and latency are the most important. Ultra reliable low latency communication we expect in like real time things, like more vehicle to vehicle communication or maybe the remote surgery. There we want it to be the ultra reliable thing as well as the low latency we expect. So there these two capabilities are important. Whereas in a massive machine type of a communication, the connection density and the network energy efficiency, these two capabilities are more important. And for enhanced mobile broadband, these all are important. So this is used 6G use scenarios where 6G is the more enhanced version of 5G. So in addition to the three early defined scenarios, uh, additional new three were introduced by ITU, that is ubiquitous connectivity, integrated AI and communication, integrated sensing and communication, and few of the design principles are also uh, introduced here. So with this six capabilities or six scenarios and these four design principles are expected from the 6G. And this particular diagram depict the same thing. The three scenarios defined for 5G, and these six are representing which are evolved from the three scenarios mentioned for the 5G. These are the six one, the same these six one, and outer circle here you can see the design principles. So this is a wheel diagram. So same way, total 9 enhanced capabilities and six capabilities defined the same way. This is palette diagram for the 6G, which is also defined by the ITU. So this diagram shows the adoption of 5G in India. So on this axis we have years, and on this axis we have uh, customers in billion. We can clearly observe from here this green graph represent the 4G rollout, and this one is for adoption graph for the 5G. So we can see to achieve 1 billion count, 4G took 6 years, whereas 5G took 4 years. So adoption rate of 5G is 2 years ahead of 4G. So and even the same this diagram shows the rollout of the 5G in different region. This particular is representing in India, even though this 5G rollout in India is huge, around 4.2 lakh BSTs are installed for 5G. Then to the current, this record is around December or November 2023, which shows only 11% of people were using 5G. But expected or projected percentage of customers by 2029 would be more, around 68%. So the key technologies used in 5G are for better signaling, means these are the 5 key. Apart from that, we have different key technologies also. OFDM for better signals. Then for efficient transmission of signal, we use MIMO, massive MIMO. For green signaling, UA oriented design. So what is meant by green signaling? So this UA-oriented design focuses on energy efficient signaling between the user device and the network, which reduces the power consumption and making the network more sustainable and suitable for long-term use. And then to increase the bandwidth, mmWave frequencies are used, and for faster response, response, low latency design is used. So these are the few key technologies for 5G. Apart from that, the other technologies could be edge computing, network slicing, network function virtualization, AI, ML, satellite integration, some other technologies. Okay, then there comes the need of quantum computing. Why we need quantum computing in next generation communication? So basically, the quantum computing see, as per the discussion, the next generation communication refers to evolving set of technologies, which I just mentioned, and the systems, next generation systems, aims to meet the increasing demand for faster, more secure, and more efficient communication. This includes the advancement like 5G and 6G networks, which promises the ultra low latency, higher data rates, massive connectivity, and new capabilities, which we have just seen. And apart from that, this new next generation systems also focus on enabling the Internet of Things, like smart cities, autonomous vehicles, and immersive experiences like virtual reality and augmented reality. So the this all means will result into the need of a quantum computing, uh, because of the mentioned challenges. The first one is security. As data, because of all this, the data privacy will be the concern, and it will grow with the increasing complexity of the systems. And whatever current encryption methods are there, they may become vulnerable to the future threats which are posed by the quantum computers. Uh, so the quantum computing through mechanics like quantum key distribution offers theoretically unbreakable encryption, ensuring the security of a communication even in face of a quantum powered attacks. Then, from network efficiency point of view, the complexity of managing vast interconnected networks with the explosion of IoT devices requires the optimized solution uh, that the current classical systems struggle to provide. So, quantum computing can potentially accelerate the data processing, improve the network traffic management, and optimize the routing protocols. Then, next is data volume and processing. So, quantum algorithms, uh, particularly in the fields of machine learning and signal processing, can provide the computational advantages needed to handle the data surge, uh, increase in the data. So, and then quantum communication and global connectivity. This could be the challenge because quantum technologies include quantum entanglement, and the quantum repeaters, and can enable the criteria of quantum internet that offers ultra secure, high speed communication across long distance. Uh, so that causes this shows the means need of quantum communication, quantum computing in the next generation communication. Uh, so the complexity and demand of this communication networks grow, and the quantum computing provides the necessary computational power and security to support and enhance the next generation communication. And that's why it's important to have to look through the quantum computing. So how it plays an important role, the quantum computing. So quantum computing plays an transformative role in the evolution of next generation communication. So it will provide you, means we can see its use in a or role in communication. So as I mentioned, the quantum superposition and entanglement, this principle enable the generation of keys for encryption and that are impossible to intercept without detection. Okay, we will see this quantum compute cryptography and post-quantum cryptography in a bit while. So also the quantums are needed in quantum communication networks. They will provide the quantum repeaters, which will overcome the distance limitation by retransmitting the quantum states and enabling the long distance quantum communication. Then quantum internet enables the secure, instantaneous global communication using quantum entanglement and the potentially support the distributed quantum computing. So these are the few things which represent that how the quantum computing is going to play a very important role in next generation communication. Even the quantum algorithms and quantum algorithms enhance the communication algorithms. That quantum algorithms can potentially be used to improve the efficiency of the communication channels, allowing for faster data processing and transmission. Also, we can use quantum to correct the uh, awa- uh, for error correction. New protocols are essentially for maintaining the quantum communication fidelity in noisy environment. Uh, okay, quantum has a role in machine learning as well as signal processing. Uh, the quantum-based quantum machine learning can accelerate the processing and analysis of large data sets, improving the task like pattern recognition, modulation scheme, and interference management in communication system. Then it also plays important role in meteorology and sensing, then also accelerating the communication networks with quantum computing. And also we have quantum enabled satellites. So I skipped this history part, maybe it is not required here. So directly jump to the quantum computing fundamentals. So in fundamentals, we have qubits, then quantum superposition, quantum entanglement, and then quantum interference, quantum noise, quantum gates. The basic building block of quantum computing is a qubit. Qubit is quantum bit. So quantum bit is a fundamental unit of quantum information, and it is analogous to the classical bits. Uh, like we have the bits which can exist in only one state, either 0 or 1. But in quantum computing, the qubit can exist in two states simultaneously. That is called as a superposition, a state of superposition, which can represent both 0 and 1 simultaneously. So it can be represented as means a qubit is represented as a linear combination of the two states. Okay, we will discuss these notations. What are this? This is called as a get 0 and this is get 1. So the qubit is a linear combination of these two states, state 0 and state 1. And these are representing the amplitudes or probability amplitudes or probability distribution. And so like this diagram may make the things more clear. The classic bits, they will have a distinct means they will have one value at a time, 100% probability. Either it can be 0 or it will be 1. So 100% probability, either of one. But qubit can be 0 or 1. So if I say it has a 50% probability, then means the coefficient here, if those are equal, then we can say that the qubit has a probability, equal probability to be go into the 0 state or 1 state. And this is entanglement. Qubits can be means the state of uh, two or more qubits are dependent on each other. So if you change the state of one bit, automatically the state of other bit will change uh, irrespective of the distance between those two. So these are the types of qubits actually. So so we have to choose a qubit based on the application, and we can categorize them based on the what type of physical system is used to define those qubits. Okay. So the notation of qubits, I'm going a bit faster because the time is already over.
Yes, ma'am. Yes, ma'am. If you want, you can take some few minutes also.
Okay. So I will cover this. So So as I mentioned, the qubits can be distinguished based on the physical system used to realize them. So I'm not going in detail about the types of those. Directly, I come to the notation or how we can represent the qubits. So in order to define a qubit, we use a bracket notation. So this symbol, a vertical line and this bracket, this denotes a column vector and it is known as a ket. Okay, this is representing a column vector and it is known as a ket, uh, called as a ket. So why it is required? So qubit is it is means qubit is a quantum computing particle that has a wave-like nature. Maybe it is there on the somewhere in next slides. So qubit is a particle that has a wave-like nature with the wave function psi x, and which satisfies this Schrodinger's equation, and that's why we use a vector representation or vector notation to represent this wave function. So in this notation, two-dimensional vector, state vector, ket1, this ket1 and ket0 are used for a qubit. Okay, so here we can say is this is a state 0, right? So which can be represented as a linear combination of these two. This is representing the probability amplitude. So which clearly say that the probability of uh, this particular bit to result into 0 state is 1, and this is representing the probability of this particular bit to result into a state of 1 is 0. So just it is just a notation where these coefficients are nothing but the probability amplitudes of the qubit, and this particular notation is called as a ket notation. This represent this particular symbol denotes the column vector, whereas this particular symbol denotes the row vector, this one row vector. Now these values just we have taken, this could be any values, okay, like alpha beta in general. So this is a row vector and this notation is called as a bra notation. Okay, in general, in common form, a single bit, a single qubit in a bracket notation can be represented like this. So in general, in quantum computing, we use a ket notation most of the times to represent a bit, a qubit. So as I mentioned, this is representing a wave function sum. Okay, a qubit is a wave function. So here this alpha and beta are in general, now again this alpha and beta are the complex coefficient, that means have a form of a plus j beta. Alpha I can write as a plus j beta. So it is a complex, in general it is a complex coefficient and which measure the probability amplitudes. The probability, so if I say alpha is equal to a j beta, then we can measure the amplitude and phase. How we can measure? We know that how to find from any complex number, we can always find its phase and amplitude. For amplitude, just we have to take the square root of squares of each of the term. Like amplitude or mod of alpha will be simply square root of a square plus beta b square, and its phase will be simply tan inverse of b by a. So like that, we can always find the probability magnitude or amplitude and phase of each of the computational state basis. These are called as a basis. This, okay. And so for and this particular constraint, that is a square plus alpha square plus beta square is equal to 1, this ensures that the total probability of measuring the qubit as a 0 or 1 is 1. So this is called as a normalized constraint, normalization constraint. So for 2 or multiple qubits, the product of those qubits is called as a tensor product. The tensor product or the Kronecker product is can be computed using this notation, the which is called as a this particular notation is used to denote the tensor product between two qubits or two or more qubits. Circle in time symbol, this one is. So if I assume two qubits like Kate A, Kate B, then their Kate A, Kate B, as I mentioned, Kate is a column vector as A0 and A1 with the coefficient A0, A1, and Kate B is a vector with the coefficient B0 and B1. So their tensor product is defined as Kate A circle in time with Kate B, and it can be found out by taking a simple multiplication with their coefficients A0 into this Kate means column vector for B, and A1 means each of the coefficient has to be multiplied to the column vectors, and we get the resultant vector. Resultant matrix will be means this will be the resultant vector, which can be simply represented or which simply represent the product of tensor product of those two qubits. So here also the normalization constraint rule is same, that is the square of each of coefficient, the addition or sum of square of each of this coefficient would result into 1, making or ensuring that the probability will be 1. Probability of taking any of the state will be always 1. So if we have 3 qubits, then tensor product of 3 bit will be simply, you can take this way, the tensor product of 3 bits. Already we have calculated for 2 qubits. Now this is for 3 qubits. And the same thing, the normalization constraint rule will be applicable here as well. And the same method will be used to combine the n qubits, and the normalization constraint will be denoted with this equation, summation vi square is equal to 1. That means summation of all these, this is y, it has to be y. Summation of square of all this coefficient will be equal to 1. So another important things about the quantum computing is Bloch sphere. Now this Bloch sphere is similar to a Pinocchio sphere in electromagnetics, where the Pinocchio sphere is used to represent a state of polarization uniquely on, means we can define any state of polarization uniquely on the Pinocchio sphere. Same way, each state, the qubit state, we can represent uniquely on this Bloch sphere. So Bloch sphere is a 3-dimensional sphere where any point on the surface of the sphere represent a unique pure state of a qubit, and this particular north pole and south pole on the sphere represent the basis states. Basis states, Ket 0 and Ket 1. The north one represent the basis 0 state, whereas the south pole represent this one, represent the basis uh, 1 state. So, and see this any quantum state can be parameterized in terms of two real angles. See, this is a sphere which is a spherical coordinate system we can use. So, spherical coordinate system we can define using r, theta and phi coordinates. So, any quantum state we can parameterize or represent in terms of this two real angles, theta which varies from 0 to pi and phi which varies from 0 to 2 pi. So, using that we can define any quantum state uh, using this particular equation, where cos theta by 2 is alpha and e j phi sin theta by 2 is beta. Just you compare this equation with this one. So alpha is your cos theta by 2 and beta is e to the power j phi sin theta by 2. So using, see the amplitudes of those coefficients are, or the probability amplitudes are dependent on this theta. This phi is not at all defining the amplitude, it is just determining the phase. Okay. So, and one more important thing, the theta will determine the latitude and phi will define the longitude. Means where exactly a particular state is going to lie on this particular sphere. So, with the example, you may understand it. So, here we can see the block sphere. Use the same equation, this equation, just substitute theta value and phi value. So, if I substitute theta 0, phi 0, this equation will reduce to this, because cos theta by 0 is 1 and sin 0 is 0. So, it will reduce and we get a basis state get 0, which is this north pole. Similarly, if I substitute theta is equal to pi and phi is equal to 0 in this equation, I will get this basis state, which is simply Ket 1. Ket 1. The same way, just substitute different values of theta and pi and you will get the location of the quantum states. So, on surface of sphere, you will get the pure states of quantum or qubits. No, rest of other are representing the other linear combinations of those basis functions. So, whatever we have discussed, the same is mentioned on the side. So, I will not repeat it. Now, coming to the quantum superposition. Quantum superposition is a fundamental principle of quantum mechanics that describes the ability of a quantum system uh, such as qubit to exist in multiple states simultaneously. Just like we discussed earlier, it can be either 0 or 1 or simultaneously, both of them. So that kind of a thing or characteristic is called as a superposition. So this already we have discussed mathematically that quantum state is represented as Ket psi, as this is a wave-like function which is given by this equation. Alpha, beta are representing the amplitudes and which satisfy this normalization constraint, that is alpha square plus beta square is 1. So, which ensures the total probability of measuring the qubit as 0 or 1 is always 1. So, before measurement, we are not aware whether which state a particular quantum or qubit will take. So, the qubit is not in a definite state, neither 0, K0 or Ket0 or neither Ket1, but rather it is, or we can say basis state 0 and 1, but rather it is in a superposition of these two states. Linear combination where coefficients are representing the probability of occurrence of that. Okay, so these two are nothing but the probability. amplitudes. So linear combination of that. So after measurement, upon measuring the qubit, the superposition collapse into one of the possible basis states, either 0 or 1, with a probability determined by the magnitudes of probability amplitudes, that is alpha square and beta square. So quantum computing, in quantum computing, superposition allows the quantum computers to perform many calculations simultaneously. The main principle behind quantum computing that is that only, na, keep performing multiple operations calculations simultaneously. So superposition thing allows the quantum computers to perform many operations simultaneously. The quantum algorithms can process this superposition of all possible inputs at once rather than having evaluate each one at a time. So same way we can define the superposition of multiple qubits. There we can represent the possible means a state as a linear combination of those two qubits. Same how we represent classical bits. Two bits आहेत 0 0 0 1 1 0 1 1. Same way. If we have two qubits, their states can be represented as a linear combination of four possible basis states. These are called as a basis state. And again, here also we have a normalization condition in this form. So the state represent a superposition of all four basis states, meaning the two qubits can be in any combination of these states simultaneously. So quantum entanglement, which is nothing but this which is the most fascinating and fundamental phenomena in quantum mechanics, where two or more quantum particles become interconnected. Interconnected, that means the state of one particle is directly related to the state of other particle, no matter how apart they are. So by using this particular mechanism, this quantum circuits are created using quantum gates. So quantum gates again are we define the quantum gates in terms of matrices, whereas the qubits we define in terms of vectors, either column vector or row vectors. So when a particular qubit passes through a gate, the resultant will be simply multiplication of these two, the vector multiplied by the matrix represented by the gate. So the another important concept in quantum computing is quantum interference. So the qubit has wave-like nature. As I mentioned, this is wave-like nature, even though we are saying it as a bit, but actually it is a the qubit has a wave-like nature, and it is described by quantum wave function, as I mentioned earlier also. So the wave function is mathematical description of quantum state that consists of already this also I have discussed complex probability amplitudes and the corresponding probabilities of the quantum states. So when we have multiple qubits, their wave functions are added together to like this. When we have multiple qubits, their wave function will get added here. This is called as a constructive interference, whereas this is destructive, opposite. No? So this is a destructive interference. So when multiple qubits, their wave functions are added together in a constructive manner, then resultant state of the quantum system is called as a interference. When it is added, when the two wave functions will get added, then we call it as a interference, constructive interference. Then the other term is a quantum noise. Quantum noise refers to the uncertainty and fluctuation that arise in a quantum system due to the probabilistic nature of the quantum mechanism. This will lead to the loss of quantum properties over the time, affecting the outcome of a quantum circuit. The common type of noise that we observe in quantum circuits are measurement noise, and the other one is a decoherence noise. So this is again means this is also again an important concept in case of quantum computing, the noise. So decoherence or this particular decoherence noise, it deals with means this particular noise, it arises when interaction means in some the systems will interact with the environment and can cause a quantum system to lose the quantum superposition or entanglement and interference, affecting the performance of the quantum algorithm. And this particular noise is called as a decoherence, and this noise has significant impact on the quantum computing. To address this challenge, uh, researchers are working on the quantum error correction techniques. And the other one is a measurement noise. This occur when measuring a quantum system, and the act of measurement can cause a quantum system to lose a quantum superposition and cause a quantum state into one of the states. So which will result into the uncertainty in the outcome. So these two kind of noise could be there in the quantum computing. So this is just an example of quantum circuit. As I mentioned, we have different quantum gates. These are single qubit gates, and these are 2 qubit gates. When a qubit passes through this gate, uh, certain operation will be performed by these gates, and the resultant will be simply the multiplication of vector, because as I mentioned, each of the gate is represented with a matrix. So multiplication, simple multiplication of, see, these are the different gates in a quantum computing. Could be a single qubit gates or 2 qubit gates. And the output would be simply the multiplication of matrix. The gate is represented with the matrices like this, matrix multiplied by the vector. Then comes the quantum algorithms. Quantum algorithms solve the computational problems more efficiently than the classic algorithms, and often uh, leverage the unique properties of quantum mechanics. Then the main aim of this quantum algorithms are to provide the solution to the problems that are computationally hard for a classic computer, especially those that involve the large data sets, complex computations, and that the problems inherently suited for the quantum speedups. So here I have listed few of the quantum algorithms, key functions, and on the next slide, very important quantum algorithms. These are very famous: Shor's algorithm, Grover's algorithm. Shor's algorithm used for efficient integer factorization, breaking classical cryptographic system like RSA, whereas Grover's algorithm, it is used for a faster search in unstructured databases. So other are also there listed over there. So here the quantum cryptography. So quantum cryptography refers to cryptographic protocols that leverage the principle of quantum mechanism to secure the communication. It uses the quantum states phenomena such as superposition, entanglement, and non-cloning theorem to provide the security to the system. Then post-quantum cryptography, see the difference here, it provides the protocols, this refers to the protocols that leverages uh, certain quantum mechanism to provide the secure communication, whereas this post cryptographic refers to the cryptographic algorithms that are designed to secure against the capabilities of quantum computer itself. So post quantum cryptographic algorithms are intended to be implemented using classical hardware and algorithms, but provide the security for the large-scale quantum computers. So here the difference between the quantum and post-quantum cryptography. As I mentioned, it focuses on quantum mechanisms for secure communication. Example of quantum cryptography is quantum key distribution cryptography, whereas post-quantum cryptography focuses on design of cryptographic algorithms that are resistant to quantum attacks. And few other differences are mentioned here for the quantum and post-quantum cryptography. So classification of quantum key distribution or quantum cryptography and post-quantum cryptography algorithms are mentioned. Very famous and popular important cryptographic algorithms. These are post-quantum cryptography. So those are classified based on the mechanism used to implement it. So implementation is basically using the quantum circuits using the quantum gates. So as I mentioned, quantum cryptography focuses on using the quantum mechanism for security, while post-quantum cryptography is focused on the developing new classical cryptographic methods that can withstand to the capabilities of future quantum computers. And each type of quantum and post-quantum cryptography plays important role in different aspects of securing communication, providing robust solution, and these are the few quantum simulators used to test and debug the quantum circuits with realistic noise models. This So challenges and future outlook, the scalability, building large scale quantum computers that are stable and can handle large real world communication problems is still an open question. Then integration with classical system, integrating the quantum communication technologies with existing classical communication infrastructure poses a significant technical challenge, especially regarding the transition between quantum and classical data processing and cost. Finally, the cost and infrastructure. Developing the quantum communication infrastructure on large scale requires significant investment in the new hardware, network design, and global cooperation. So in conclusion, we can say that the quantum computing is still experimental stage, and many technological challenges remain, such as qubit stability, error correction and stability. But it is a rapidly growing field with potential to revolutionize computing, secure communication, and optimize the network performance, enabling the new application. And as the quantum technologies mature, we are likely to see the integration of quantum methods into the mainstream communication system. Thank you for patient listening.
Thank you, ma'am. Respected ma'am, I would like to express my sincere gratitude for enlightening the session on quantum computing and secure communication. Your expertise and passion for this subject definitely inspire us, and it would appreciate the time you took to share your knowledge with us. Your presentation has significantly enhanced our understanding of the potential of quantum computing and its application in secure communication. So we are very grateful for your valuable insights and contribution to our learning. So thank you again for your outstanding presentation. And one more, yes, ma'am.
No, sir. Go ahead.
Participant have some question and you can ask. Is anybody want to ask a question?
It's almost 10 o'clock.
Yes, ma'am. Yes, ma'am. Once again, thank you. And one more announcement to all the participant. Participant have to fill the attendance and feedback link that is already posted in the chat session. And for tomorrow, so there are two important sessions, one from Mr. Swapnil Kulkarni from United Kingdom and another from Dr. Sridhar Prabhuraman. It is from Sydney, Australia. So I hope that you will join on time for tomorrow's session. So this is from today's session. So I conclude that this session is over. Thank you very much.